Here is the uncomfortable truth. Every diagram you've ever seen of Earth's orbit around the Sun is fundamentally wrong. They show a simple ellipse, a closed loop that returns to the same place each year. But Earth has never returned to the same location in space, not once in 4.5 billion years. The Sun itself is racing through the galaxy at 20 kilometers per second, dragging our entire solar system along a path that creates a spiral through three-dimensional space. Tonight, we'll trace Earth's true trajectory with quiet precision, following our planet's motion through galactic rotation, solar system dynamics, and the expanding universe itself. We'll move from familiar textbook orbits to the reality measured by Gaia and Hipparchus, so Earth's path stops looking like a simple circle and starts revealing the elegant helix it actually traces through the cosmos. You and I will move forward one careful step at a time, allowing the true picture to settle clearly until it becomes natural to see how our planet spirals through space without ever retracing its steps. And we begin with part 1. Why does every science textbook show Earth's orbit as a simple closed loop when reality tells a completely different story? The educational materials lining classroom walls across the world display our planet's path as an elegant ellipse, returning each year to precisely the same cosmic coordinates where it began. These wire models suspended from classroom ceilings reinforce this deceptive simplicity, showing Earth tracing the same predictable route around a motionless sun, year after year, century after century. Students absorb this fundamental misconception without questioning whether such perfect repetition actually occurs in the vast complexity of space. The truth reveals itself when we examine what these teaching aids actually represent versus what they claim to show. Educational diagrams serve as convenient simplifications designed to help young minds grasp basic orbital mechanics without drowning in the overwhelming reality of cosmic motion. They strip away layers of complexity that would otherwise make learning impossible at introductory levels. However, somewhere between pedagogical necessity and scientific accuracy, profound misunderstanding takes root. Students graduate believing our solar system exists in splendid isolation, with planets dutifully returning to identical starting positions as calendar years tick by. This static universe assumption becomes so deeply embedded in our thinking that most adults never question whether Earth actually retraces its steps through space. The wire orbit models hanging in physics classrooms inadvertently teach that cosmic motion resembles a closed racetrack rather than an open highway stretching across the galaxy. When teachers demonstrate planetary motion using these physical models, they unknowingly reinforce the illusion that orbital mechanics occurs within a stationary reference frame. The psychological impact of this educational approach cannot be overstated. Human brains naturally seek patterns and closure, finding comfort in cycles that repeat predictably. The idea that Earth returns home each year appeals to our desire for cosmic stability and familiar rhythms. We instinctively think orbit equals returning to starting point, because our daily experience involves circular or cyclical motions that bring us back to recognizable locations. Walking around a city block returns us to our starting corner. Driving around a traffic circle brings us back to our entry point. These terrestrial experiences create mental templates that we unconsciously apply to celestial mechanics, leading us to assume that orbital motion must follow similar closed-loop patterns. The educational system reinforces this misconception by presenting orbital diagrams without proper context about reference frames or the broader cosmic environment. Students learn about elliptical paths and gravitational forces without understanding that the entire stage upon which this celestial dance unfolds is itself racing through space at incredible velocities. Textbooks show Earth and other planets as though they exist within a cosmic snow globe, isolated from the dynamic galactic environment that actually shapes their motion. This fundamental misrepresentation creates a gap between classroom physics and astronomical reality that most people never bridge. The consequences extend beyond mere academic curiosity. When space agencies plan missions to other planets, they must account for the true complexity of orbital mechanics, incorporating not just planetary motion around the Sun, but also the solar system's movement through the galaxy. Navigation systems for deep space probes require sophisticated calculations that acknowledge what classroom models ignore. Nothing in the cosmos remains stationary, and therefore nothing truly returns to where it started. Every sunrise illuminates an Earth positioned at completely novel cosmic coordinates millions of kilometers away from its location during the previous year's corresponding sunrise. This revelation challenges our fundamental assumptions about place, position, and the nature of cosmic cycles, setting the stage for a deeper exploration of how Earth actually moves through the vast expanse of space. Could it be that Earth has never, in its entire 4.5 billion year history, returned to the same location in space even once? This staggering realization shatters our comfortable assumptions about planetary motion and forces us to confront an uncomfortable truth that challenges everything we thought we knew about our cosmic address. When we celebrate each new year, marking what feels like Earth's completion of another orbital cycle, our planet actually finds itself positioned millions of miles away from where it occupied space during the previous year's festivities. The champagne corks that pop at midnight herald not a return to the familiar cosmic territory, but rather Earth's arrival at completely virgin coordinates in the vast expanse of the universe. Every sunrise that greets our eyes illuminates a world that has never before witnessed daybreak from that precise location in space, making each dawn a unique cosmic event that will never be repeated throughout the remaining lifespan of our solar system. This profound reality emerges when we account for a crucial factor that textbooks consistently omit. Our sun refuses to remain stationary in the galaxy, but instead races through the Milky Way at the breathtaking velocity of 20 kilometers per second, equivalent to 140 miles every single second of every single day. To appreciate the magnitude of this galactic sprint, imagine traveling from New York to Los Angeles in just 20 seconds, and you begin to grasp the incredible speed at which our entire solar system hurtles through space. The sun drags Earth and all its planetary siblings along on this epic galactic journey, creating a cosmic caravan that never pauses, never slows, and never reverses direction to retrace its steps through the star-filled void. This relentless forward motion transforms what appears to be Earth's simple elliptical orbit around the Sun into something far more magnificent and complex. A sweeping helical spiral that corkscrews through three-dimensional space as our world simultaneously circles the Sun and races alongside it through the galaxy. Picture a stone thrown from a speeding train, and you glimpse the type of curved trajectory that Earth actually follows, except our cosmic train never stops at any station, and our planetary stone never hits the ground, but continues spiraling forward through space for billions of years. The mathematical reality of this motion defies easy visualization, because human brains evolved to navigate terrestrial landscapes, not to comprehend the simultaneous rotation, revolution, and galactic translation that defines our true cosmic choreography. When ancient, philosophers pondered the fundamental question of where exactly we are in the universe. They possessed more wisdom than they realized, for this query touches upon one of the most profound aspects of cosmic mechanics. Our location cannot be defined by any fixed cosmic landmarks, because no such landmarks exist in a universe where everything moves relative to everything else. The very concept of absolute position becomes meaningless when we recognize that space itself lacks any stationary reference points from which to measure our coordinates. Earth's helical path through the galaxy resembles a cosmic Neystrand, twisting and spiraling as it advances through space in a pattern so complex that even sophisticated computer simulations struggle to capture its full beauty. Each loop of this cosmic helix represents 1 year of Earth's orbital dance around the Sun. But unlike the closed loops depicted in classroom diagrams, these spirals never intersect or repeat because the entire pattern advances through space at galactic velocities. The pitch of this helix depends upon the ratio between Earth's orbital speed around the Sun and the solar system's velocity through the galaxy, creating a three-dimensional sculpture of planetary motion that stretches across light-years of space. Modern astronomical observations confirm this helical reality through precise measurements of stellar positions and motions. When astronomers track the apparent movement of distant stars over decades and centuries, they detect tiny shifts that reveal not only the star's own motion through space, but also the solar system's journey through the galaxy. These observations provide direct evidence that we never return to the same cosmic neighborhood, never retrace our steps through the star fields that surround us. The implications extend far beyond academic astronomy into practical considerations for space exploration and navigation. When mission planners calculate trajectories for spacecraft, traveling to distant planets or moons They must account for the fact that both Earth and their targets will have moved to entirely different galactic coordinates by the time the spacecraft completes its journey. This cosmic reality transforms space travel into a complex exercise in multidimensional navigation that would be impossible without supercomputers capable of tracking the simultaneous motions of multiple celestial bodies racing through an ever-changing galactic environment. What if we could trace Earth's genuine trajectory through the cosmos using the most advanced instruments ever deployed in space, revealing a cosmic dance so intricate that it transforms our understanding of where we truly reside in the universe? Tonight's exploration will guide us through multiple reference frames, each unveiling another layer of Earth's complex motion as we journey from the familiar spin of our daily rotation to the mind-bending reality of cosmic expansion itself. This adventure requires us to shift our perspective repeatedly, like adjusting the zoom on a cosmic telescope, pulling back from terrestrial viewpoints to galactic scales and beyond until we comprehend the full scope of our planet's perpetual voyage through space-time. The European Space Agency's revolutionary Gaia mission stands as humanity's most ambitious attempt to map our galactic neighbourhood with unprecedented precision, tracking over 1 billion stars to create a three-dimensional atlas of stellar positions and velocities that reveals the intricate choreography of our cosmic surroundings. This extraordinary spacecraft, positioned at a gravitationally stable point between Earth and the Sun, continuously scans the heavens with instruments so sensitive they could detect the width of a human hair viewed from 1,000 kilometers away. Gaia's observations penetrate the veil of stellar motion that has puzzled astronomers for centuries, measuring tiny shifts in star positions that betray not only their individual movements through space but also the solar system's own journey through the galactic disk. These measurements achieve accuracies measured in microarcseconds, equivalent to observing a coin on the moon's surface from Earth, providing the foundation for understanding how our entire cosmic neighbourhood flows through space like a vast river of stars. NASA's deep space observatories contribute complementary pieces to this cosmic puzzle, with missions like the Hubble Space Telescope, James Webb's Space Telescope, and various interplanetary probes confirming the complex nature of our cosmic trajectory through direct observations and navigation data. When spacecraft travel to distant planets, mission controllers must constantly recalculate trajectories to account for the fact that both Earth and target destinations occupy completely different galactic coordinates as months and years pass during these interplanetary journeys. The Voyager probes, now sailing through interstellar space, beyond the influence of our solar system, provide direct measurements of how our stellar neighbourhood moves relative to the surrounding galaxy, sending back data that confirms theoretical predictions about our cosmic motion. These robotic explorers serve as humanity's first messengers to venture beyond our solar cocoon, carrying with them the capability to measure our galactic environment from perspectives impossible to achieve from Earth's surface. Understanding our cosmic address matters profoundly for both practical space exploration and fundamental questions about our place in the universe, as accurate knowledge of Earth's true path enables precise navigation for future missions while revealing the dynamic nature of cosmic structure on every scale. The implications cascade through multiple fields of science, from geology and climate studies that must account for long-term changes in Earth's galactic environment to astrobiology investigations seeking to understand how our planet's journey through different galactic regions might influence the evolution of life over geological timescales. Ancient civilizations gazed upward at seemingly fixed constellations, unaware that these stellar patterns slowly shift and distort as our solar system travels through the galaxy, creating an ever-changing celestial landscape that unfolds over timescales far exceeding human lifespans. Modern astronomy reveals that the very concept of fixed stars represents an illusion born from our limited temporal perspective, as every celestial object participates in the grand cosmic ballet of galactic rotation and universal expansion. Tonight's journey will synthesize these discoveries into a coherent picture of Earth's helical trajectory, connecting the dots between daily rotation, annual revolution, galactic orbital motion, and cosmic expansion to reveal how our planet spirals through space-time in patterns of breathtaking complexity and beauty. We shall explore how Earth's path interweaves with the motions of companion planets, creating a cosmic tapestry where each world traces its own unique helix, while remaining gravitationally bound to our travelling solar family. The revelation awaiting us challenges conventional notions of repetitive cycles and closed loops, replacing them with an understanding of Earth as a cosmic voyager on an endless journey through ever-changing galactic landscapes. This perspective transforms our relationship with time and space, revealing how each moment of our lives unfolds at cosmic coordinates that have never before been occupied and will never again be revisited throughout the remaining billions of years of our solar system's existence. The mathematics describing these nested motions demonstrates the elegant unity underlying apparent chaos, showing how physical laws governing motion at every scale combine to create the magnificent spiral path that carries our world through the cosmos. As we prepare to how can our planet hurtle through space at velocities that would tear apart any human-made machine, yet we remain blissfully unaware of this incredible cosmic roller coaster beneath our feet? Earth's rotation generates surface speeds that boggle the mind, with points along the equator racing eastward at 170 km per hour or 1,000 miles per hour, a velocity sufficient to traverse the entire width of Texas in under 90 minutes. This phenomenal speed varies dramatically depending upon your latitude, creating a fascinating gradient of rotational velocities that decreases steadily as you travel toward either pole. Standing at the equator places you on the fastest moving real estate our planet offers, while venturing to the North or South Pole brings your rotational speed to absolute zero, creating the curious situation where polar explorers experience no rotational motion whatsoever, despite occupying the same spinning world as their equatorial counterparts. The mathematical relationship governing this, latitudinal speed variation follows the cosine of your latitude, meaning that mid-latitude locations like New York or London experience roughly 75% of the equatorial rotational velocity, while cities closer to the Arctic Circle move at increasingly slower rates until reaching the poles where rotation ceases entirely. This incredible motion remains imperceptible to our senses because of a fundamental principle that revolutionized physics. Objects moving at constant velocity within a closed system experience no sensation of movement. We evolved aboard this spinning world, developing within an inertial reference frame that masks the tremendous forces involved in planetary rotation. Our inner ears, designed to detect acceleration rather than constant motion, register no signal indicating we rocket through space at supersonic speeds. The air surrounding us spins along with the solid Earth, creating an atmospheric envelope that moves in perfect synchronization with the surface below, eliminating any wind effects that might betray our true velocity. However, subtle evidence of this rotation manifests in phenomena that early scientists used to prove Earth's motion centuries before space travel confirmed the obvious. The Coriolis effect emerges as perhaps the most elegant demonstration of our planetary spin, deflecting moving objects to the right in the northern hemisphere and left in the southern hemisphere due to the rotating reference frame we inhabit. This mysterious force influences everything from weather patterns and ocean currents to the trajectory of ballistic missiles, creating curved paths that would be impossible on a stationary world. Long-range artillery gunners must calculate Coriolis corrections to hit distant targets accurately, while meteorologists rely on this effect to understand cyclone formation and atmospheric circulation patterns. Modern global positioning system satellites provide another compelling example of technology that must accommodate Earth's rotation to function properly. These orbital spacecraft continuously broadcast timing signals that ground receivers use to calculate precise positions, but the calculations become meaningless unless engineers account for the fact that both satellites and receivers participate in Earth's relentless eastward spin. The satellites themselves orbit at altitudes where they experience slightly different gravitational fields than surface dwellers, requiring additional relativistic corrections that highlight how rotation interweaves with the fundamental structure of space-time itself. Historical debates about Earth's shape and motion take on new significance when viewed through the lens of rotational mechanics. Ancient flat Earth proponents struggle to explain why objects dropped from great heights land directly below their release points, rather than falling westward as the Earth allegedly rotated beneath them. This puzzle remained unsolved until scientists realized that dropped objects inherit the eastward velocity of their release location, maintaining their rotational momentum as they fall and thus landing precisely where intuition suggests they should. The resolution of this paradox helped establish the principle of inertia, while simultaneously confirming Earth's rotation through logical reasoning rather than direct observation. Foucault pendulums demonstrate rotational effects through their slow precession over the course of a day, as the pendulum's swing plane remains fixed in space while Earth rotates beneath it, creating the illusion that the pendulum gradually changes direction, when in reality our entire laboratory rotates around the stationary oscillation. These elegant devices transformed abstract concepts about planetary motion into tangible demonstrations that anyone could witness, providing definitive proof that we inhabit a spinning world even when our senses suggest otherwise. What mysterious force causes our seemingly stable planet to wobble, like a gigantic spinning top over vast stretches of time, creating celestial changes so gradual that entire civilizations rise and fall before completing a single cycle? Earth's rotational axis executes a slow, majestic precession that requires approximately 26,000 years to complete one full wobble, a phenomenon that transforms our view of the heavens across millennia while remaining virtually invisible to observers tracking changes over human lifespans. This cosmic wobble emerges from gravitational interactions between our tilted, rotating planet and the combined pulling forces exerted by both the Sun and Moon, which attempt to straighten Earth's axial tilt, but instead create the gyroscopic response that characterizes all spinning objects subjected to external torques. The physics underlying this precession mirrors the behavior of a child's spinning top, which responds to gravitational nudges not by falling over immediately, but rather by tracing slow circles as its axis maintains its angular momentum while yielding to outside influences. Earth's equatorial bulge, caused by centrifugal forces that make our planet slightly wider at the equator than at the poles, provides the gravitational handle that allows solar and lunar tidal forces to grip our world and induce this cosmic wobble. The Sun attempts to pull the equatorial bulge toward the ecliptic plane, while the Moon exerts similar torques from its inclined orbital position, creating a complex gravitational tug-of-war that results in the smooth precession we observe today. This celestial dance produces profound consequences for astronomy and navigation, most notably causing the position of the celestial pole to drift slowly through the northern constellations over thousands of years. Currently, the bright star Polaris serves as our North Star, sitting conveniently close to the point where Earth's rotational axis intersects the celestial sphere. But this fortunate alignment represents merely a temporary cosmic coincidence that will not persist indefinitely into the future. Ancient Egyptian astronomers oriented their pyramids and temples using different pole stars than those available to modern observers, while future generations will navigate by entirely different stellar beacons as precession carries the celestial pole through its slow journey across the sky. The star Vega, currently shining in the constellation Lyra, will assume the role of northern pole star approximately 12,000 years from now, while Thuban in Draco held this position when the Great Pyramid of Giza was constructed over 4,000 years ago. Ancient civilizations possessed sufficient astronomical knowledge to detect and record this gradual shift, with careful observers in Egypt, Mesopotamia, and Greece noting discrepancies between star positions recorded by earlier generations and their own contemporary observations. The Greek astronomer Hipparchus first quantified this motion around 130 BCE by comparing his measurements with Babylonian records made centuries earlier, discovering what he termed the precession of the equinoxes. This discovery revealed that even the seemingly eternal stars participate in slow cosmic dances that unfold over timescales far exceeding individual human experience. Modern climate science recognizes Earth's wobble as one component of the Milankovitch cycles, which describe how variations in our planet's orbital and rotational characteristics influence long-term climate patterns and ice age cycles. The 26,000-year precession cycle interacts with changes in Earth's orbital eccentricity and axial obliquity to create complex patterns of solar heating that drive glacial and interglacial periods over geological timescales. When precession aligns Northern Hemisphere summer with Earth's closest approach to the Sun, enhanced seasonal contrasts promote ice accumulation at high latitudes, while the opposite alignment tends to produce warmer conditions that melt existing ice sheets. Scientists studying paleoclimatology examine ice cores, marine sediments, and other geological records to trace how these astronomical cycles have influenced Earth's climate throughout its history. Very long baseline interferometry represents the pinnacle of modern technology for measuring Earth's precession, with extraordinary precision, employing networks of radio telescopes separated by thousands of kilometers to track minute changes in our planet's orientation relative to distant quasars. These cosmic beacons, located billions of light years away, serve as nearly perfect reference points for detecting Earth's wobbles and precession, because their immense distances render them essentially motionless from our perspective. VLBI measurements achieve accuracies measured in microarc seconds, equivalent to detecting the width of a human hair viewed from a distance of several kilometers, allowing scientists to monitor not only the steady precession of Earth's axis, but also smaller wobbles and irregularities caused by atmospheric circulation, ocean currents, and even the redistribution of mass during major earthquakes. The data collected through these sophisticated observations contribute to our understanding of Earth's internal structure, rotational dynamics, and the complex interactions between solid Earth, atmosphere, and oceans that influence our planet's motion through space. Why does defining motion become impossible without first deciding what we consider stationary? And how does this fundamental challenge reveal that absolute stillness represents nothing more than a persistent illusion embedded within human perception? The universe refuses to provide any fixed landmarks against which we might measure genuine rest, forcing scientists to confront an uncomfortable reality that every description of movement depends entirely upon our chosen reference framework. This conceptual puzzle becomes immediately apparent when we attempt to describe something as basic as Earth's daily rotation, which appears completely different depending upon whether we measure it relative to distant stellar backgrounds or relative to our local sun. When astronomers track our planet's spin using remote stars as reference points, they discover that Earth completes one full revolution in precisely 23 hours and 56 minutes, a duration known as the sidereal day because it represents the time required for any given star to return to the same position in our sky. However, measuring the same rotational period using the sun as our reference yields the familiar 24-hour solar day that governs human schedules and calendar systems worldwide. This 4-minute discrepancy between sidereal and solar days arises because Earth simultaneously rotates on its axis while orbiting around the sun, requiring our planet to spin slightly more than 360 degrees each day to bring the sun back to the same apparent position. Picture Earth as a carousel horse that must complete one extra rotation to face the same direction relative to a distant observer who slowly walks around the entire carousel, and you begin to grasp why solar and sidereal days differ in duration. This seemingly minor distinction carries profound implications for navigation, astronomy, and our understanding of cosmic reference frames. Navigators aboard ships and aircraft must account for this difference when using celestial observations to determine their position, while astronomers rely upon sidereal time to predict when specific stars will become visible above the horizon. The 4-minute daily accumulation between solar and sidereal time creates an annual shift that causes star maps to become gradually obsolete unless updated to reflect changing celestial coordinates. Constellations visible at midnight during winter slowly migrate across the sky throughout the year, eventually becoming daylight objects hidden behind the sun's glare before reappearing in evening skies months later. This celestial choreography results directly from Earth's orbital motion around the sun, which changes our perspective on the surrounding stellar background as we travel through different regions of space during our annual journey. Ancient astronomers puzzled over these shifting star patterns for millennia before recognizing that they provided evidence for our planet's motion through space rather than indicating movement by the stars themselves. Modern physics owes much to Einstein's revolutionary insight that motion remains fundamentally relative, with no experiment capable of determining absolute velocity through space without reference to external objects or fields. Special relativity emerged from the recognition that describing motion requires choosing a reference frame, and that no frame possesses special status as absolutely stationary. Whether we consider Earth rotating beneath a fixed stellar backdrop, or envision the entire universe as spinning around a stationary Earth, becomes a matter of mathematical convenience rather than physical truth. Both descriptions yield identical predictions for observable phenomena, though one proves vastly simpler for practical calculations than the other. This relativity principle extends far beyond Earth's rotation to encompass all forms of motion throughout the cosmos, from subatomic particles to galactic clusters racing through intergalactic space. The absence of absolute reference points transforms questions about motion into exercises in selecting appropriate coordinate systems for specific problems. Satellite engineers typically employ Earth-centered coordinates when planning orbital maneuvers, while planetary scientists prefer sun-centered frameworks for calculating interplanetary trajectories. Stellar astronomers adopt galactic coordinate systems when mapping our local cosmic neighborhood, and cosmologists invoke universal expansion models when studying the largest scales of space and time. Each reference frame reveals different aspects of the same underlying reality, like examining a sculpture from multiple viewpoints to appreciate its complete three-dimensional form. The challenge of describing Earth's motion without absolute reference points foreshadows even greater complexities that emerge when we consider larger-scale movements involving our entire solar system's journey through galactic space. Just as daily rotation appears different when measured against stars versus the Sun, our annual orbit around the Sun transforms into something far more intricate when viewed from galactic perspectives that reveal the whole solar system's motion through the Milky Way. These nested reference frames create layers of motion that compound upon each other, making Earth's true path through space a magnificent spiral that defies simple description while demonstrating the elegant complexity of cosmic mechanics operating across multiple scales simultaneously. What would happen to human consciousness if we could somehow perceive the staggering velocity at which our seemingly tranquil planet rockets through space during its annual pilgrimage around our local star? Earth maintains a blistering pace of 107,000 kilometers per hour, equivalent to some thousand miles per hour, or approximately 30 kilometers every second, as it traces its elliptical pathway through the solar system in a cosmic marathon that spans nearly 1 billion kilometers from start to finish each calendar year. This tremendous velocity dwarfs the fastest speeds achieved by human transportation, making supersonic aircraft appear motionless by comparison, while rocket ships seem to crawl at glacial rates relative to our planet's natural orbital momentum. The sheer magnitude of distances involved in this celestial voyage challenges human comprehension, as Earth covers roughly 2.6 million kilometers every single day, a distance equivalent to traveling around our planet's circumference more than 60 times between consecutive sunrises. Our world's pathway forms an ellipse rather than a perfect circle, creating fascinating variations in solar distance that produce counterintuitive seasonal effects often misunderstood by casual observers. Perihelion occurs during early January when Earth approaches its closest point to the Sun at approximately 47 million kilometers, while aphelion takes place in early July when our planet reaches its most distant orbital position at roughly 152 million kilometers from our central star. This 5 million kilometer difference in solar distance creates a paradox for Northern Hemisphere inhabitants who experience their coldest months precisely when Earth occupies its nearest solar approach, while enduring peak summer heat during our planet's most remote orbital phase. The resolution of this apparent contradiction reveals that axial tilt rather than orbital distance governs seasonal temperature patterns, with the 23.5 degree inclination of Earth's rotational axis determining which hemisphere receive more direct solar radiation throughout different portions of our annual journey. Kepler's laws of planetary motion provide elegant mathematical descriptions of how orbital velocity varies according to distance from the central gravitating body, explaining why Earth accelerates to maximum speed during the January perihelion passages while decelerating to minimum velocity during July aphelion phases. These velocity variations amount to several thousand kilometers per hour difference between fastest and slowest orbital phases, creating subtle but measurable effects on day length and stellar positions that ancient astronomers detected using primitive instruments. The elliptical nature of planetary orbits emerges from the delicate balance between gravitational attraction and angular momentum conservation, with each world maintaining just enough sideways velocity to avoid spiraling into the Sun while lacking sufficient speed to escape solar gravitational influence entirely. Modern spacecraft. Navigation requires sophisticated calculations that account for Earth's continuous orbital motion, as mission planners must predict where planets will be positioned months or years in the phases when robotic explorers finally reach their destinations. Launching a probe toward Mars involves aiming not at the red planet's current location, but rather at the precise coordinates it will occupy, after accounting for both Earth's and Mars's orbital advancement during the lengthy interplanetary cruise phase. This complex celestial billiards demands supercomputer modeling that tracks multiple moving targets while calculating optimal launch windows that minimize fuel requirements and mission duration. The European Space Agency's recent Bepi-Colombo mission to Mercury required 7 years of intricate orbital mechanics involving multiple planetary flybys to gradually adjust the spacecraft's heliocentric velocity and reach the innermost planet's extreme solar vicinity. Such missions demonstrate how Earth's orbital motion serves simultaneously as both launching platform and a navigational challenge, providing initial velocity for escaping our gravitational well while creating moving reference points that complicate trajectory calculations. Ground-based observatories must also compensate for our planet's orbital movement when tracking distant astronomical objects, as annual parallax shifts caused by Earth's changing position relative to remote stars enable astronomers to measure cosmic distances using trigonometric methods pioneered centuries ago. The combination of rapid orbital velocity and vast distances travelled reveals Earth as an incredibly dynamic platform, hurtling through space at speeds that would terrify any conscious passenger aware of the tremendous forces involved in maintaining our stable yet high-speed trajectory around our life-giving stellar companion. How does a mere 23.4-degree inclination of our planet's rotational axis relative to its orbital plane orchestrate the magnificent symphony of seasons that governs life on Earth, while simultaneously creating one of astronomy's most elegant celestial reference systems? This seemingly modest angular deviation between Earth's spin axis and its pathway around the Sun generates the profound climatic variations that transform our world from the icy grip of winter into the warmth of summer, demonstrating how subtle geometric relationships can produce dramatic environmental consequences across our planet's surface. The tilted nature of Earth's rotational axis means that different hemispheres receive varying amounts of direct solar radiation throughout our annual journey, with the northern hemisphere experiencing peak summer conditions precisely when our planet occupies its most distant orbital position from the Sun during early July. This counterintuitive relationship between seasonal temperature and solar distance confounds casual observers who logically assume that closer proximity to our central star should produce warmer conditions, yet the reality demonstrates that axial orientation, rather than orbital distance, controls the intensity of solar heating received by different terrestrial regions. When the northern hemisphere tilts toward the Sun during summer months, solar rays strike the surface at steep angles that concentrate energy over smaller areas while extending daylight hours to maximize thermal input, creating the warm conditions we associate with summer despite Earth's relatively remote orbital position. Conversely, when the same hemisphere tilts away from the Sun during winter months, solar radiation arrives at shallow angles that spread the same energy over larger surface areas, while reducing daylight duration to minimize heating, producing frigid conditions even though Earth has moved closer to the Sun than at any other time during the year. Ancient civilizations recognized these patterns of changing daylight duration and solar elevation long before understanding the underlying astronomical mechanics, constructing elaborate monuments and observatories to track the Sun's apparent annual migration across the sky. Stone circles like Stonehenge and megalithic sites throughout Europe demonstrate sophisticated knowledge of solstices and equinoxes, with architectural alignments precisely marking the extreme positions of sunrise and sunset that occur when Earth's tilted axis creates maximum and minimum solar angles for different latitudes. The summer solstice represents the moment when the northern hemisphere achieves its maximum tilt toward the Sun, producing the longest day and shortest night of the year for northern observers, while simultaneously creating the winter solstice conditions of shortest day and longest night for southern inhabitants. Equinoxes mark the transitional moments when Earth's axis tilts neither toward nor away from the Sun, creating equal day and night durations worldwide as our planet occupies specific positions in its orbital path where the terminator line separating day from night passes directly through both poles. The ecliptic plane, defined by Earth's orbital pathway around the Sun, serves as a fundamental reference system for astronomy and celestial navigation, providing the baseline against which astronomers measure the positions and motions of planets, moons, comets, and asteroids throughout the solar system. This geometric plane extends infinitely in all directions from the Sun, creating a cosmic coordinate system that enables precise descriptions of celestial object locations and trajectories. Most major planets orbit within a few degrees of the ecliptic plane, suggesting that our solar system formed from a flattened disk of material that retained its original orientation during planetary accretion processes billions of years ago. Modern satellite observations confirm the remarkable precision of Earth's orbital mechanics through continuous monitoring of our planet's position relative to the Sun and distant stars, with the space-based instruments measuring minute variations in orbital parameters that reveal subtle influences from other planets and the complex gravitational environment of our solar neighbourhood. The global positioning system relies upon precise knowledge of Earth's orbital motion to maintain accuracy, as satellites must account for relativistic effects caused by their high velocities and altered gravitational fields relative to surface observers. Climate monitoring satellites track seasonal changes in solar heating patterns that result from our planet's axial inclination, providing detailed measurements of how energy distribution varies with latitude and season to create the complex weather systems that characterize different terrestrial environments. These observations validate theoretical models of orbital mechanics while revealing the intricate connections between astronomical geometry and terrestrial climate that make Earth uniquely suitable for supporting diverse life forms across its varied landscapes and seasonal cycles. What cosmic choreography aligns 8 distinct worlds into a flattened disk arrangement that preserves the original architecture of our solar system's formation, while creating subtle gravitational interactions that influence planetary motion across geological timescales. The remarkable coplanarity of planetary orbits within our solar neighbourhood results from the collapse of an ancient protoplanetary disk, where swirling gas and dust condensed into the diverse collection of terrestrial and gas giant worlds we observe today. This fundamental geometric arrangement means that Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all pursue their individual journeys within approximately the same celestial plane, creating the illusion that wandering stars follow a predictable pathway across our night sky. Ancient astronomers noted this phenomenon long before understanding its physical origins, mapping the zodiacal constellations through which planets regularly travel as they execute their complex orbital dances against the stellar background. The ecliptic plane serves as astronomy's primary coordinate system precisely because it represents the fundamental organizational structure of our cosmic neighborhood, providing a reference framework against which we measure all other celestial motions and positions. However, this apparently simple planar arrangement conceals intricate gravitational interactions that create subtle but measurable perturbations in planetary orbits over extended periods. Jupiter's immense gravitational influence reaches across the solar system to affect every other world, including Earth, whose orbital characteristics undergo slow modifications as our massive planetary neighbour completes its 12-year journey around the Sun. These Jovian perturbations alter Earth's orbital eccentricity over cycles lasting approximately 100,000 years, sometimes making our planet's path more circular and other times stretching it into a more elongated ellipse that changes the intensity of seasonal contrasts. The gravitational tugs exerted by Venus and Mars also contribute to long-term variations in Earth's orbital parameters, creating complex cyclical patterns that climate scientists study to understand natural climate variability across geological timescales. These planetary influences cause Earth's orbital orientation to precess slowly through space, shifting the timing of perihelion and aphelion passages relative to seasonal cycles and creating the astronomical foundation for ice age periodicity. Mathematical models describing these multibody gravitational interactions require sophisticated computer simulations that track millions of years of planetary motion to predict how orbital characteristics evolve over time. The intricate dance of gravitational forces extends beyond simple two-body interactions to include resonances where planets develop synchronized orbital relationships that either stabilize or destabilize their motion depending upon specific frequency ratios. Jupiter's gravitational shepherding has carved gaps in the asteroid belt through resonant clearing mechanisms while protecting Earth from frequent impacts by deflecting or capturing potentially hazardous objects before they can threaten our biosphere. The giant planet's presence in the outer solar system acts as a cosmic vacuum cleaner, removing debris that might otherwise bombard inner planets with catastrophic consequences for life's development. Saturn contributes its own gravitational influence to this protective system, while simultaneously maintaining the complex ring structures that demonstrate how celestial mechanics operates across vastly different spatial scales. Uranus and Neptune, despite their remote positions, participate in the gravitational symphony that shapes long-term planetary evolution through subtle perturbations that accumulate over millions of orbital cycles. Modern space missions have refined our understanding of these planetary interactions through precise navigation data collected during interplanetary voyages, revealing discrepancies between predicted and observed spacecraft trajectories that indicate previously unknown gravitational effects. The recent New Horizons mission to Pluto required course corrections based upon improved models of outer planet masses and positions, demonstrating how our knowledge of solar system dynamics continues evolving through direct exploration. Space-based observatories like the Kepler telescope have discovered thousands of exoplanetary systems that exhibit similar planar arrangements suggesting that disk-like configurations represent universal outcomes of star and planet formation processes throughout the galaxy. These discoveries provide comparative context for understanding our own solar system's architecture, while revealing the diversity of possible planetary arrangements that exist elsewhere in the cosmos. Yet beneath this apparent orderliness lies a stunning revelation that transforms our perspective on a planetary motion. This entire carefully orchestrated system of worlds participates in an even grander journey through galactic space, carrying all planets along as passengers aboard a cosmic vessel that never retraces its path through the star-filled void surrounding us. What if discovering our solar system's true velocity through the galaxy reveals that Earth has embarked upon a cosmic journey so vast that all of recorded human history represents merely an infinitesimal fraction of a single lap around our celestial neighbourhood? The Sun, far from remaining stationary as terrestrial observations might suggest, rockets through galactic space at the breathtaking speed of 20 kilometers per second, equivalent to 40 miles every heartbeat, dragging our entire planetary family along on an epic voyage that dwarfs all earthly concepts of distance and duration. This incredible galactic velocity carries us around the Milky Way's central region in a majestic orbital dance that requires between 220 and 250 million terrestrial years to complete just one revolution, a time span so enormous that it challenges human comprehension while providing profound perspective on the relationship between cosmic and biological evolution. Consider the staggering implications of this galactic chronometry. When Earth last occupied its current position relative to the galaxy's spiral structure, our planet existed in the early Triassic period, an alien world where primitive archosaurs were just beginning to diversify into the lineages that would eventually produce dinosaurs, crocodiles, and birds. The supercontinent Pangaea dominated Earth's geography during that distant galactic spring, while the first mammals remained tens of millions of years in the future, and flowering plants had not yet evolved to transform terrestrial ecosystems. Every familiar aspect of our modern biosphere emerged during our solar system's current galactic orbit, from the rise and fall of dinosaurian dynasties to the emergence of grasslands, the evolution of primates, and the eventual appearance of human civilization within the last cosmic microsecond of this 250 million year journey. The distance separating us from the galaxy's central region spans approximately 26,000 light-years, positioning our solar system roughly halfway between the Milky Way's dense core and its outer edge in a region known as the Orion Arm, or local spur. This intermediate location provides Earth with a relatively stable gravitational environment, avoiding both the chaotic central regions where stellar encounters and supernova explosions occur frequently and the sparse outer zones where heavy elements necessary for planetary formation remain scarce. Our galactic neighbourhood contains hundreds of billions of stellar companions, each following its own complex orbital trajectory through the galaxy's gravitational field, while participating in the larger pattern of galactic rotation that maintains the spiral structure visible in other galaxies throughout the universe. The concept of galactic years provides a temporal framework for understanding evolutionary processes on scales that dwarf geological epochs, revealing how biological innovation and extinction events unfold against the backdrop of our solar system's cosmic voyage. Dinosaurs dominated terrestrial ecosystems for roughly 1 to 5 million years, representing about 2/3 of our current galactic orbital period, while modern humans have existed for perhaps 300,000 years, equivalent to barely 1,000th of a galactic revolution. Written human history spans mere millennia, an interval so brief relative to galactic timescales that it resembles a single tick of a cosmic clock measuring eons rather than seconds. This perspective transformation helps explain why astronomical phenomena appear constant from human viewpoints while actually changing dramatically over the extended durations required for galactic motion to become apparent. The stellar constellations that guided ancient navigators and inspired mythological traditions will gradually distort and dissolve as individual stars follow divergent galactic orbits, creating entirely different sky patterns for future civilizations lucky enough to witness Earth's next passage through this same galactic longitude millions of centuries hence. Modern measurements of our galactic motion rely upon observations of distant quasars and galaxies that serve as fixed reference points for detecting the solar system's movement through space, revealing not only our orbital velocity around the galactic center, but also smaller scale motions that reflect gravitational interactions with nearby stellar groups and dark matter concentrations. The European Space Agency's Gaia mission has revolutionized our understanding of galactic dynamics by precisely measuring the positions and velocities of over 1 billion stars, creating a three-dimensional map of stellar motions that reveals the complex choreography underlying galactic structure and evolution. Why does the band of the Milky Way appear to sweep across our night sky at such a dramatic angle, rather than following the same pathway that planets trace through the zodiacal constellations? And what does this celestial geometry reveal about our solar system's orientation within galactic space? The answer lies in a remarkable 60-degree inclination between our solar system's orbital plane and this galaxy's primary disk, creating a cosmic misalignment that transforms Earth's simple annual revolution around the Sun into an intricate three-dimensional spiral that weaves through galactic space like a cosmic DNA helix. This steep angular relationship means that our familiar ecliptic plane, along which planets appear to march across terrestrial skies, cuts through the galactic disk at a sharp angle rather than lying parallel to the Milky Way's structure. When we observe the luminous band of our galaxy, stretching across dark skies from horizon to horizon, we are peering edge-on through the galactic disk from our tilted vantage point, explaining why this stellar river appears to flow at such a steep angle relative to the planetary pathways visible in our night sky. The 60-degree inclination creates fascinating consequences for Earth's motion through galactic space, as our planet's annual orbit around the Sun causes us to alternately lead and lag behind our central star's position in its galactic trajectory. During approximately half of each terrestrial year, Earth races ahead of the Sun along the galactic orbit, while during the remaining months, our world trails behind its stellar companion as we complete our annual dance around our local gravitational anchor. This cosmic choreography produces measurable variations in Earth's velocity through galactic space, with our planet achieving maximum galactic speed during June, when our orbital motion around the Sun aligns with the solar system's direction of travel through the galaxy. Conversely, December brings minimum galactic velocity, as Earth's orbital motion opposes the Sun's galactic trajectory, creating a seasonal rhythm in our cosmic speed that adds another layer of complexity to our planet's journey through space. The mathematical description of these velocity variations reveals Earth's galactic speed fluctuating between approximately 200 and 250 km per second as our orbital position relative to the Sun's galactic motion changes throughout the year. These measurements represent the vector sum of our orbital velocity around the Sun, combined with the solar system's motion through galactic space, demonstrating how nested reference frames create complex patterns of movement that require sophisticated analysis to fully understand. The European Space Agency's groundbreaking Gaia mission has provided unprecedented precision in measuring these galactic motions through observations of stellar parallax and proper motion that reveal how our entire solar neighbourhood moves through space. This remarkable spacecraft, positioned at the gravitationally stable Lagrange point between Earth and the Sun, continuously scans the heavens with instruments sensitive enough to detect angular motions equivalent to watching a coin on the Moon's surface from Earth's distance. Gaia's measurements confirm theoretical predictions about our solar system's tilted orientation, while revealing subtle variations and perturbations that result from gravitational interactions with nearby stellar groups and dark matter concentrations. The mission's data processing requires accounting for Earth's complex motion through space, as the spacecraft shares our planet's orbital journey around the Sun, while participating in the broader galactic voyage that carries our entire stellar neighbourhood through the Milky Way's gravitational field. These observations demonstrate how local motions within the solar system combine with larger-scale galactic dynamics to create the intricate pattern of Earth's true path through space. The tilted nature of our solar system relative to the galactic plane suggests that our planetary family formed from a molecular cloud that possessed its own angular momentum independent of the galaxy's rotational structure, preserving this original orientation throughout the 4.6 billion years since planetary accretion began. This geometric relationship influences our perspective on galactic structure, making certain regions of the Milky Way more easily observable than others, depending upon our seasonal position and the angle at which we view different galactic directions. Radio astronomers exploit these viewing angle changes throughout the year to map galactic structure and study phenomena like hydrogen gas distribution and pulsar populations that reveal the galaxy's hidden architecture. The complex three-dimensional pattern traced by Earth's motion through galactic space creates a helical trajectory that never repeats, ensuring that our planet continuously explores virgin cosmic territory as it spirals forward through the star-filled void surrounding our solar system. Could there be a hidden connection between our solar system's vertical bouncing motion through the galactic disk and the mysterious mass extinction events that have periodically devastated life on Earth throughout geological history? Beyond our primary orbital journey around the galaxy's centre, our solar system executes a fascinating secondary motion that carries us alternately above and below the Milky Way's central plane in a cosmic oscillation resembling the gentle bobbing of a cork on ocean swells. Currently, we find ourselves ascending through galactic space at approximately 7 kilometers per second, climbing steadily away from the dense stellar populations and interstellar material, concentrated within the galaxy's primary disk structure. This vertical migration carries our solar neighbourhood through regions of varying stellar density, gas concentrations, and cosmic ray flux that may influence conditions within our planetary system over millions of years. The complete cycle of this galactic oscillation requires roughly 60 million years from one extreme to the other, meaning that our solar system alternately spends approximately 30 million years above the galactic plane and another 30 million years below it, before crossing back through the disk's central region. Intriguingly, this C-million-year periodicity corresponds remarkably closely to patterns observed in Earth's fossil record, where major extinction episodes appear to occur with suspicious regularity that has puzzled paleontologists for decades. Some researchers have proposed that our passage through the denser central regions of the galactic disk exposes Earth to increased cosmic radiation, gravitational perturbations from nearby stars, and enhanced comet bombardment from the outer solar system that could trigger biological crises. The physical mechanisms underlying these potential connections remain subjects of active scientific investigation, with competing hypotheses attempting to explain how galactic environment variations might influence terrestrial climate and biosphere stability. Our present position places us approximately 20 light-years above the galactic plane, having crossed through the disk's central region roughly 3 million years ago during the Pliocene epoch, when early human ancestors were beginning to walk upright across African savannas. This timing coincidence, while likely purely fortuitous, demonstrates how our cosmic journey intersects with evolutionary milestones in Earth's biological development. Current trajectory calculations predict that our solar system will continue climbing for several million more years until reaching maximum elevation of approximately 300 light-years above the galactic plane, positioning us well beyond the densest concentrations of interstellar matter that characterize the Milky Way's star-forming regions. From this lofty galactic vantage point, our solar neighbourhood will pause momentarily before gravity begins drawing us back toward the central plane, initiating a long descent that will carry us through the disk and eventually to equivalent distances below the galactic equator. The forces driving this vertical oscillation arise from the galaxy's gravitational field, which acts like a cosmic spring that restores displaced objects toward the central plane while allowing them to overshoot and continue oscillating indefinitely. Mathematical models describing this motion treat the galactic disk as a gravitating sheet whose restoring force increases linearly with distance from the central plane, creating simple harmonic oscillations similar to that exhibited by masses attached to terrestrial springs. However, the reality proves more complex due to spiral arm structures, molecular cloud distributions, and dark matter concentrations that create asymmetries and perturbations in the galactic gravitational field. These complications introduce variations in oscillation amplitude and period that make precise predictions challenging over extended timescales. Observational evidence for this vertical motion comes from studies of stellar kinematics that reveal systematic patterns in how stars move perpendicular to the galactic plane, with different stellar populations showing varying oscillation amplitudes depending upon their ages and formation histories. Younger stars like our Sun typically exhibit smaller oscillation amplitudes than older, stellar populations that formed when the galaxy possessed different structural characteristics. The density variations encountered during our vertical journey through galactic space create measurable changes in the local interstellar environment, influencing everything from cosmic ray exposure to gravitational perturbations that might affect the outer reaches of our solar system, where comets reside in vast reservoirs surrounding our planetary neighbourhood. Some theoretical studies suggest that passage through dense molecular clouds could alter the heliosphere's structure, potentially allowing increased cosmic radiation to penetrate the inner solar system and influence atmospheric chemistry or climate patterns on Earth and other planets. What breathtaking cosmic choreography emerges when we combine Earth's daily rotation, annual orbital revolution, and our solar system's relentless galactic voyage into a single unified description of our planet's actual trajectory through the universe. The mathematical synthesis of these multiple simultaneous motions reveals that Earth traces an elegant helical pathway through space, resembling a cosmic Neystrand that spirals forward through the whole galaxy without ever retracing its steps or returning to previously occupied coordinates. This magnificent corkscrew pattern results from the superposition of our planet's circular orbital motion around the Sun with the linear galactic translation that carries our entire solar neighbourhood through the Milky Way at a tremendous velocity. Imagine Earth as a bead sliding along a wire coil that itself moves steadily through space, and you begin to visualise the beautiful helical geometry that characterises our world's true cosmic journey. The pitch of this cosmic helix depends upon the ratio between Earth's orbital speed around the Sun and our solar system's velocity through galactic space, creating loops that complete one full turn every terrestrial year, while advancing roughly 19 million kilometres in the galactic direction during that same interval. Each revolution of this spectacular spiral carries Earth approximately 940 million kilometres around the Sun, while simultaneously transporting us forward through virgin galactic territory that no previous Earth orbit has ever explored. The combined daily displacement of our planet through space totals an astounding 21.6 million kilometres, comprising 2.6 million kilometres of orbital advancement around the Sun, plus 9 million kilometres of galactic progression toward the constellation Cygnus. These tremendous distances dwarf all earthly concepts of travel, making Earth the ultimate cosmic voyager that never pauses, never rests, and never reverses direction during its epic journey through the star-filled void. The concept of returning to where we were a year ago becomes completely meaningless when viewed from this galactic perspective, as Earth's previous annual position now lies millions upon millions of kilometres behind our current location in space. Last year's summer solstice occurred at cosmic coordinates that our planet will never revisit throughout the remaining billions of years of our solar system's existence, making every moment of every day a unique cosmic event unfolding at previously unexplored locations in the universe. This revelation transforms our understanding of planetary motion from simple cyclical repetition to dynamic cosmic exploration, where Earth serves as humanity's natural spacecraft carrying us forward through an ever-changing galactic landscape. The mathematical description of helical motion requires vector calculus to properly account for the multiple rotational and translational components that define our planet's trajectory, with each coordinate requiring complex equations that incorporate Earth's axial rotation, orbital revolution, solar galactic motion, and various perturbations from gravitational interactions with neighbouring celestial bodies. Parametric equations describing this helical path reveal how Earth's position in three-dimensional space changes continuously as functions of time, creating curves of breathtaking mathematical elegance that capture the essence of cosmic motion at its most fundamental level. Computer simulations capable of visualizing these trajectories demonstrate the striking beauty of Earth's helical journey, showing how our seemingly chaotic combination of motions resolves into graceful, spiraling patterns that extend across galactic distances. These visualizations help bridge the gap between abstract mathematical descriptions and intuitive understanding of how planetary motion actually unfolds within the broader galactic context. Modern astronomy relies upon precise knowledge of these helical trajectories for calculating spacecraft navigation, predicting satellite positions, and understanding how Earth's changing galactic environment might influence long-term climate patterns or cosmic radiation exposure. The recognition that Earth follows a helical rather than cyclical path through space also affects our interpretation of astronomical observations, as phenomena that appear periodic from terrestrial perspectives may actually represent encounters with different regions of galactic space during successive loops of our cosmic spiral. This perspective shift influences everything from stellar parallax measurements to studies of interstellar medium variations that our solar system encounters during its galactic voyage. The helical nature of Earth's motion through space provides a unifying framework for understanding how local planetary dynamics connect with galactic-scale physics, revealing our planet as an integral participant in the grand cosmic dance that encompasses scales from subatomic to universal, all governed by the same fundamental physical principles that shape motion throughout the observable universe. How does the vector addition of Earth's orbital velocity and our solar system's galactic motion create a cosmic speedometer that fluctuates dramatically throughout the year, yet remains completely imperceptible to human senses despite reaching velocities that would obliterate any terrestrial vehicle? The fascinating interplay between our planet's 30 km per second orbital speed around the Sun and our solar system's 220 km per second journey through galactic space produces a complex velocity profile that varies seasonally as these two motion vectors alternately reinforce and oppose each other. During June, when Earth's orbital trajectory aligns with our solar system's galactic heading, these velocities combine constructively to propel our planet through space at approximately 250 km per second, a breathtaking speed that would circumnavigate our entire globe in roughly 2.5 minutes. Conversely, December brings the opposite configuration, where Earth's orbital motion directly opposes our galactic trajectory, reducing our net velocity through the Milky Way to roughly 200 km per second, as the two motion components partially cancel each other. This 50 km per second seasonal variation represents a tremendous change in cosmic velocity that dwarfs the performance capabilities of any human-engineered propulsion system, yet it occurs so smoothly that no terrestrial experiment can detect this acceleration without reference to external astronomical objects. The mathematical treatment of velocity combination requires vector analysis rather than simple arithmetic addition, as the angular relationship between orbital and galactic motion vectors determines how these speeds compound or interfere. Earth's orbital plane tilts 60 degrees relative to our galactic trajectory, creating a geometry where the maximum and minimum velocity combinations occur at specific times of year when the projection of our orbital motion onto the galactic direction reaches its extreme values. This vectorial relationship produces a sinusoidal variation in Earth's galactic speed that peaks during northern summer and reaches its minimum during northern winter, creating a cosmic rhythm that connects seasonal cycles with our journey through interstellar space. The physics underlying our inability to perceive these tremendous velocities stems from Einstein's principle of relativity, which demonstrates that uniform motion cannot be detected from within a moving reference frame without external markers for comparison. Earth, its atmosphere, and everything upon its surface participates equally in these cosmic motions, creating an inertial environment where no internal experiment reveals our true velocity through space. This principle explains why early astronomers struggled to detect Earth's motion around the Sun, as the planet's atmospheric envelope and everything within it moves together as a unified system that masks the tremendous speeds involved in planetary and galactic motion. The seasonal velocity variations occur gradually enough that Earth experiences negligible acceleration during these transitions, maintaining the inertial conditions that keep passengers aboard our cosmic vessel blissfully unaware of the incredible speeds at which they travel. Modern physics recognizes that acceleration rather than velocity produces detectable effects within moving systems, and Earth's smooth progression through its velocity cycles creates accelerations so tiny that they remain far below the threshold of human perception or measurement using terrestrial instruments. The sophisticated mathematical framework of special relativity governs how different observers measure space and time intervals, revealing that simultaneity, distance, and duration depend upon the observer's motion relative to the phenomena being measured. These relativistic effects become significant only at velocities approaching the speed of light, but they provide the conceptual foundation for understanding why Earth's tremendous galactic speed remains undetectable from our planetary perspective. Global Positioning System satellites must account for relativistic corrections that result from their orbital velocities and gravitational environments, demonstrating how even modest speeds by cosmic standards can produce measurable effects when precision requirements demand extraordinary accuracy. The seasonal variation in Earth's galactic velocity creates subtle relativistic effects that influence high-precision astronomical observations, requiring corrections that account for how our changing velocity affects the apparent positions and frequencies of distant celestial objects. Stellar aberration represents one observable consequence of Earth's motion, as starlight appears to shift direction slightly due to our planet's velocity relative to distant stellar sources, creating annual patterns that reveal our orbital motion around the Sun and provide indirect evidence for the underlying physics governing motion in relativistic space-time. The elegant mathematical description of these velocity combinations demonstrates how local planetary dynamics connect seamlessly with galactic scale phenomena, revealing the underlying unity that characterizes motion throughout the cosmos, from subatomic to universal scales, all governed by the same fundamental principles that Einstein articulated in his revolutionary theories of relativity. What extraordinary technological achievements allow modern astronomers to measure stellar positions with such incredible precision that they can detect motions equivalent to observing a human hair from the distance of the Moon? And how do these measurements confirm our understanding of Earth's helical journey through galactic space? The European Space Agency's revolutionary Gaia Observatory represents humanity's most ambitious attempt to map our cosmic neighbourhood, continuously scanning the heavens from its gravitationally stable position at the Lagrange point between Earth and the Sun while tracking the positions and motions of more than 1 billion stars with unprecedented accuracy. This remarkable spacecraft employs advanced CCDs cooled to near absolute zero and sophisticated optical systems that achieve angular resolution, measured in micro-arcseconds, a precision so extraordinary that it could distinguish between two fireflies separated by the width of a coin viewed from a distance of several thousand kilometers. Gaia's parallax measurements exploit the subtle apparent motion of nearby stars caused by Earth's changing perspective as our planet orbits the Sun, using the diameter of Earth's orbit as a cosmic baseline to triangulate distances to stellar neighbours through pure geometric methods that require no assumptions about stellar properties or brightnesses. These parallactic shifts reveal themselves as tiny elliptical motions traced by stars across the celestial sphere, with closer objects exhibiting larger apparent displacements and more distant stars showing progressively smaller angular excursions that challenge the limits of observational technology. The mission's extraordinary precision enables distance determinations accurate to within a few percent for stars located hundreds of light-years from Earth, creating a three-dimensional map of our galactic neighbourhood that transforms flat star charts into detailed spatial models revealing the true architecture of local cosmic structure. Proper motion studies conducted by Gaia demonstrate galactic rotation through systematic patterns in stellar velocities that confirm theoretical predictions about how gravitational forces shape the motion of stars within the Milky Way's disk. These observations reveal that stars closer to the galactic centre orbit faster than those in outer regions, following the same differential rotation patterns that characterise spiral galaxies throughout the universe and providing direct observational evidence for the dark matter halos that dominate galactic mass distributions. The aberration of starlight provides another crucial piece of evidence for our solar system's motion through space, as the apparent positions of distant stars shift slightly due to the combination of light's finite speed and Earth's velocity relative to stellar sources. This relativistic effect creates annual patterns in stellar positions that mirror Earth's orbital motion around the Sun, while also revealing the solar system's journey through galactic space through systematic shifts that accumulate over years of careful observation. Bradley's original discovery of stellar aberration in the 18th century provided the first direct proof of Earth's orbital motion, while modern high-precision measurements reveal additional components that betray our solar system's galactic trajectory and rotation. Gaia's unprecedented data quality has enabled the discovery of previously unknown structures within the Milky Way, including a pronounced warp in the galactic disk that precesses like a cosmic spinning top over timescales of hundreds of millions of years. This warping phenomenon, caused by gravitational interactions with satellite galaxies and dark matter substructures, demonstrates that our galaxy's disk is far from the simple flat structure depicted in textbook illustrations, revealing instead a dynamic three-dimensional entity that evolves continuously under complex gravitational influences. The precession of this galactic warp occurs faster than theoretical models predicted, suggesting ongoing interactions with external gravitational sources that continue shaping our galaxy's structure on cosmic timescales. These discoveries vindicate century-old theoretical predictions while revealing new complexities that challenge our understanding of galactic dynamics and evolution. Kapteyn's early studies of stellar motions provided hints of galactic rotation that Gaia now confirms with exquisite detail, demonstrating how patient observational astronomy gradually unveils the true nature of cosmic structure through accumulated measurements spanning generations of dedicated observers. The mission's data processing requires sophisticated algorithms that account for Earth's complex motion through space, as the spacecraft shares our planet's orbital journey around the Sun, while participating in the broader galactic voyage that carries our entire stellar neighbourhood through the Milky Way's gravitational field. These computational challenges highlight how local planetary dynamics interconnect with galactic-scale phenomena, requiring comprehensive models that capture motion across vastly different spatial and temporal scales to extract meaningful scientific conclusions from raw, observational data that chronicles our cosmic journey through space and time. What profound philosophical and practical implications emerge when we realize that every cosmic address continuously changes, making the very concept of a fixed location in the universe fundamentally meaningless? Our traditional understanding of Earth's position as a simple satellite orbiting the Sun provides a comforting but incomplete description that fails to capture the dynamic reality of planetary motion within galactic space. The accurate cosmic address for our world must acknowledge that Earth spirals forward through the Milky Way as an integral component of a solar system that never returns to previously occupied galactic coordinates. This revelation transforms our perspective from a static geocentric or heliocentric model to a dynamic galactic framework where planetary motion represents just one layer of cosmic choreography unfolding across multiple scales simultaneously. The absence of truly stationary reference points anywhere in the observable universe forces us to abandon intuitive notions of absolute position and embrace the reality that all motion must be described relative to chosen coordinate systems rather than fixed landmarks. Even the most distant galaxies participate in the universal expansion that carries them away from each other at velocities proportional to their separation distances, ensuring that no cosmic milestone remains permanently fixed in space. This fundamental mobility extends from subatomic particles to galactic clusters, revealing a universe where stability emerges from dynamic equilibrium rather than static positioning. Ancient star charts gradually become obsolete because stellar positions shift continuously as individual stars follow their own orbital trajectories around the galactic centre, at velocities that differ based on their distances from the Milky Way's core. The constellation patterns that guided Polynesian navigators across Pacific waters and inspired Greek mythological traditions will slowly distort and dissolve over millennia as component stars diverge along separate galactic paths. Hipparchus detected this stellar drift in the 2nd century BCE when comparing his observations with earlier Babylonian records, discovering the precession of equinoxes without understanding its connection to Earth's axial wobble, or the broader context of galactic motion that underlies all celestial movement. Modern astronomers must regularly update star catalogues to reflect proper motions that accumulate over decades of observation, while navigation systems require sophisticated corrections that account for multiple layers of cosmic motion affecting spacecraft trajectories. Mission planners calculating routes to distant planets cannot simply aim for current target positions, but must predict where destinations will be located months or years in the future when robotic explorers finally reach their intended coordinates. The New Horizons mission to Pluto exemplified this challenge, requiring course corrections based on refined models of outer planet masses and positions that accumulated small errors over the 9-year journey to the dwarf planet's orbit. Similarly, the Voyager probe's grand tours of the outer solar system demanded intricate gravitational assist maneuvers that exploited precise planetary alignments occurring at specific times, demonstrating how cosmic clockwork enables or constrains human exploration depending upon our understanding of celestial mechanics. Deep space navigation relies upon pulsar timing arrays that provide cosmic lighthouses whose regular radio pulses serve as reference signals for determining spacecraft positions. Yet even these exotic stellar remnants drift slowly through galactic space while spinning down over geological timescales. The philosophical implications of universal motion challenge fundamental assumptions about permanence and stability that underlie human concepts of home, place, and belonging. If every coordinate in space continuously changes, what meaning can we assign to concepts of returning home or revisiting familiar locations? The house where you spent childhood occupies entirely different cosmic coordinates today than it did during your youth, having travelled billions of kilometres through galactic space during the intervening years. This perspective shift parallels ancient philosophical debates about whether one can step into the same river twice, extending the metaphor to cosmic scales where even the riverbank itself moves through space at tremendous velocities. Modern physics embraces this dynamism through relativity theory, which demonstrates that space and time form an integrated fabric that curves and flexes in response to matter and energy distributions, creating a universe where geometry itself evolves continuously. The cosmic microwave background provides our closest approximation to a universal reference frame, representing the cooled remnant of the Big Bang that pervades all space with nearly uniform radiation carrying subtle temperature fluctuations that reveal our motion relative to this primordial afterglow. Measurements of this cosmic motion indicate that our local group of galaxies moves at roughly 600 kilometers per second toward the Great Attractor, a massive concentration of galactic clusters whose gravitational influence affects cosmic motion across hundreds of millions of light years. This discovery demonstrates how local motions connect with large-scale cosmic structures, revealing Earth as a participant in hierarchical flows that encompass progressively larger volumes of space-time, from planetary orbits to universal expansion patterns governed by dark energy and cosmic evolution. How does the profound mismatch between human cognitive capabilities and cosmic reality create fundamental barriers to understanding our true path through space? And why do our evolved perceptual systems fail so dramatically when confronted with the intricate choreography of planetary motion? Our brains develop sophisticated neural networks for navigating terrestrial environments, where objects move predictably along surfaces, through air or across water, creating mental frameworks optimized for tracking motion within gravitational fields and atmospheric conditions that bear no resemblance to the frictionless vacuum of space. These evolutionary adaptations excel at processing visual information about walking animals, flying birds, or flowing rivers, but they struggle desperately when asked to comprehend multiple simultaneous rotations and translations occurring across vastly different scales without familiar reference points. The cognitive machinery that enables us to catch thrown balls, avoid predators, and navigate complex landscapes becomes utterly overwhelmed when confronted with Earth's helical trajectory through galactic space, where our planet simultaneously spins on its axis, orbits the Sun, and races through the Milky Way while participating in additional motions involving galactic oscillation and cosmic expansion. Human visual systems evolved to interpret motion within three-dimensional terrestrial settings, where up and down remain constant, objects fall toward the ground, and movement typically occurs along relatively simple trajectories that can be extrapolated from brief observations. Space motion violates these fundamental assumptions by eliminating preferred directions, gravitational anchors, and the atmospheric drag that makes terrestrial motion predictable and comprehensible to biological nervous systems. The mathematical description of helical planetary motion requires parametric equations involving trigonometric functions, vector calculus, and coordinate transformations that exceed the computational capabilities of unaided human cognition, demanding external tools to visualize relationships that remain invisible to direct perception. Computer simulations have become indispensable for revealing the true cosmic choreography underlying planetary motion, employing sophisticated algorithms to calculate and display the complex trajectories that emerge when multiple motions combine across astronomical scales. These digital models can slow time, change perspectives, and highlight specific components of motion that would otherwise remain hidden within the overwhelming complexity of real cosmic dynamics. NASA's Scientific Visualization Studio produces stunning animations that transform abstract mathematical descriptions into comprehensible visual narratives, showing how Earth's spiral path weaves through galactic space while maintaining its orbital relationship with the Sun. These computational tools enable viewers to adopt impossible vantage points outside the solar system, watching from galactic perspectives as our planetary family traces its helical journey through star-filled space. Modern educational systems face unprecedented challenges when attempting to convey three-dimensional helical motion to students whose intuitive understanding of movement derives from terrestrial experience, with objects that follow simple parabolic arcs under gravitational influence. Traditional teaching methods rely heavily on physical models and analogies that inevitably oversimplify cosmic motion, creating mental frameworks that must later be dismantled and rebuilt to accommodate the true complexity of astronomical dynamics. Interactive computer graphics and virtual, Reality environments offer promising approaches for overcoming these pedagogical obstacles, allowing students to experience cosmic motion from multiple reference frames while manipulating variables that control different components of planetary movement. However, these technological solutions remain limited by the fundamental constraint that human brains cannot simultaneously track multiple complex rotational and translational motions without becoming cognitively overwhelmed. Historical resistance to complex motion models reflects this perceptual limitation, as astronomers and physicists repeatedly favoured simpler explanations that aligned with human intuition rather than embracing mathematical descriptions that accurately captured observational data. Ptolemaic epicycles represented elaborate attempts to preserve Earth-centred cosmology by adding layers of circular motion that could account for planetary observations while maintaining familiar conceptual frameworks. Copernican heliocentrism simplified celestial mechanics by placing the Sun at the centre of planetary orbits, but it still depicted motion as occurring within a static cosmic framework that ignored galactic dynamics. Even after Galileo's telescopic observations confirmed planetary motion around the Sun, scientific communities required centuries to fully embrace the implications of universal motion that extends from local planetary systems to cosmic expansion on the largest scales. The development of increasingly sophisticated visualization technologies continues revealing new aspects of cosmic motion that challenge human comprehension. From computer models showing galactic collision sequences unfolding over billions of years, to simulations depicting dark matter flows that shape cosmic structure through gravitational interactions invisible to direct observation. These tools demonstrate how scientific progress depends upon extending human cognitive capabilities through technological augmentation, rather than relying solely upon evolved perceptual systems that proved adequate for terrestrial survival, but remain woefully inadequate for understanding cosmic reality. What colossal forces could accelerate our entire galaxy, along with dozens of neighbouring galactic systems, at velocities exceeding 600 km per second, toward an inevitable cosmic collision that will fundamentally reshape the local group's architecture in the distant future? The Milky Way participates in gravitational dynamics that extend far beyond its own stellar boundaries, racing through intergalactic space as part of a cosmic caravan comprising over 50 galaxies bound together by mutual gravitational attraction and shared evolutionary destiny. Our galactic home approaches the magnificent Andromeda Galaxy at approximately 110 km per second, guaranteeing a spectacular merger approximately 4.5 billion years from now that will create a single elliptical galaxy from the collision of these two massive, spiral systems. This approaching galactic embrace represents just one component of larger-scale motions that carry our local group through cosmic structures spanning hundreds of millions of light-years, revealing how gravitational influence operates across scales that dwarf individual galactic dimensions. The Great Attractor lurks beyond the obscuring dust clouds of the Milky Way's disk, exerting tremendous gravitational pull that draws our local group and thousands of neighbouring galaxies toward the Virgo cluster and its associated supergalactic structures. This massive concentration of dark matter and luminous galaxies creates gravitational fields strong enough to influence cosmic motion across distances exceeding 200 million light-years, demonstrating how large-scale structure formation continues shaping the universe billions of years after the initial cosmic expansion began. Modern astronomical surveys have mapped vast filaments of galaxies stretching across cosmic voids, creating a web-like architecture where matter flows along preferred pathways connecting dense nodes of galactic concentration. Our local group slides along one of these cosmic highways, carried by gravitational currents that channel galactic motion through the largest structures known to exist in the observable universe. Even more mysterious forces may influence cosmic motion through phenomena dubbed dark flow, where observations suggest coherent bulk motion affecting galaxy clusters across scales approaching the cosmic horizon. These measurements remain controversial because they challenge standard cosmological models that predict increasingly isotropic motion on larger scales. Yet multiple independent studies detect systematic velocity patterns that extend far beyond the reach of known gravitational sources. The cosmic microwave background provides our most fundamental reference frame for measuring motion through the universe, representing the cooled remnant of primordial radiation that once filled space when the cosmos first became transparent approximately 380,000 years after the Big Bang. This ancient afterglow pervades all space with nearly uniform intensity, carrying subtle temperature fluctuations that preserve information about cosmic structure formation during the universe's infancy, while serving as an absolute reference against which all other motion can be measured. Detailed analysis of microwave background radiation reveals a dipole pattern caused by our motion relative to this primordial photon field, indicating that our local group moves at roughly 627 km per second toward the constellation Leo. When astronomers subtract the known motion of Earth around the Sun and the Sun's orbit through our galaxy, they find that our planet moves at approximately 38 km per second relative to the cosmic microwave background, providing our most accurate measurement of Earth's motion through the universe as a whole. This velocity represents the sum of all nested motions from planetary orbit through galactic rotation to cosmic expansion effects, creating a comprehensive accounting of how our world participates in universal dynamics spanning scales from local solar systems to the observable cosmic horizon. The remarkable precision of these measurements demonstrates how modern cosmology can track motion across the entire hierarchy of cosmic structure, from Earth's daily rotation through galactic superclusters to the expanding space-time fabric that carries distant galaxies beyond the reach of gravitational interaction. These observations reveal Earth as an integral participant in cosmic evolution, sharing the universal expansion that began with the Big Bang, while experiencing additional motions imposed by gravitational clustering that has created the rich tapestry of cosmic structure we observe throughout the universe today. What invisible cosmic violence has twisted our galaxy's majestic disk into a warped structure resembling a gigantic potato chip that wobbles through space like an enormous cosmic spinning top? The Milky Way's disk deviates dramatically from the flat spiral structure depicted in astronomy textbooks, instead exhibiting pronounced undulations that rise and fall by thousands of light-years above and below the theoretical galactic plane. This spectacular warping phenomenon extends throughout the outer regions of our galaxy, creating a three-dimensional sculpture of stellar motion that defies simple geometric description while revealing the turbulent gravitational history that shaped our cosmic neighborhood over billions of years. The European Space Agency's Gaia mission revolutionized our understanding of this galactic distortion by precisely measuring stellar positions and velocities across vast regions of the Milky Way, discovering that the warp exhibits dynamic behavior previously unknown to astronomical science. Rather than maintaining a static configuration, this cosmic distortion precesses around the galactic center like a massive gyroscope, completing one full wobble every 600 to 700 million years in a stately cosmic dance that spans timescales comparable to complex life's evolution on Earth. The rate of this precession exceeds theoretical predictions based on standard galactic models, suggesting that additional gravitational influences beyond simple dark matter halos drive the warp's evolution through mechanisms that remain partially mysterious to contemporary astrophysics. Current research indicates that past collisions with smaller satellite galaxies provide the most plausible explanation for both the warp's existence and its unexpectedly rapid precession rate, as gravitational encounters with these cosmic interlopers would impart angular momentum and tidal distortions capable of reshaping the Milky Way's structure. These galactic interactions represent episodes of cosmic cannibalism where our galaxy's superior gravitational influence gradually dismantled and consumed smaller neighbouring systems, incorporating their stellar populations while preserving evidence of these ancient encounters in the form of persistent structural distortions. The discovery of stellar streams throughout the galactic halo provides direct observational evidence for this violent history, as these elongated trails of stars mark the disrupted remains of dwarf galaxies that wandered too close to the Milky Way's gravitational sphere of influence. The Sagittarius dwarf elliptical galaxy currently undergoes this destructive process, shedding stars in long arcs that wrap completely around our galaxy while gradually spiraling toward eventual complete disruption and absorption. Archaeological astronomy techniques allow researchers to reconstruct the timing and magnitude of past galactic collisions as by analyzing stellar age distributions, chemical compositions, and kinematic patterns that preserve signatures of ancient merger events in the present-day stellar population. These investigations reveal that the Milky Way experienced a major collision approximately 10 billion years ago with a galaxy dubbed Gaia Enceladus, which contributed significant amounts of stellar mass to our galaxy's halo, while potentially triggering enhanced star formation rates in the disk. More recent encounters with smaller satellite systems continue influencing galactic structure through ongoing tidal interactions that stretch and compress different regions of the stellar disk. The Large and Small Magellanic Clouds represent the most prominent current satellite galaxies, whose gravitational influence contributes to maintaining and modifying the galactic warp through their orbital motion around the Milky Way. Computer simulations demonstrate how repeated passages of these satellite systems through the galactic disk can excite and sustain warping modes that persist for hundreds of millions of years after the initial gravitational perturbation. Our solar system occupies a relatively stable region within the inner galactic disk, where the amplitude of warping remains minimal compared to the dramatic distortions affecting outer stellar populations located beyond 40,000 light-years from the galactic center. This fortunate positioning shields Earth from the most extreme consequences of the galactic's structural instability, while allowing our planet to maintain its habitable climate over geological timescales. The inner disk's stability results from higher stellar densities and stronger gravitational binding that resist tidal disruption from external influences, creating a cosmic safe haven where planetary systems can evolve without catastrophic disturbance from large-scale galactic dynamics. Nevertheless, the warped nature of our cosmic home demonstrates that even apparently stable galactic environments participate in ongoing evolutionary processes driven by gravitational interactions spanning cosmic scales, revealing the dynamic character of structures that appear static, from limited human temporal perspectives, but actually undergo continuous modification through forces operating over millions and billions of years. How can an invisible cosmic scaffold comprising 85% of our galaxy's total mass remain completely undetectable to human senses while simultaneously orchestrating the motion of every visible star, planet, and particle of gas throughout the Milky Way's vast expanse? Dark matter forms an enormous spherical halo that extends far beyond the visible stellar disk, creating a gravitational framework that shapes galactic structure through forces we cannot directly observe, but whose effects permeate every aspect of cosmic dynamics. This mysterious substance interacts gravitationally with ordinary matter while remaining electromagnetically neutral, making it invisible to telescopes that rely upon detecting photons emitted or absorbed by conventional atoms and molecules. The evidence for dark matter's existence emerges from detailed studies of galactic rotation curves, which reveal that stars in outer regions orbit far faster than predictions based solely on visible matter distributions would allow. Without the additional gravitational influence provided by dark matter halos, these rapidly moving stars should escape their host galaxies rather than maintaining stable circular orbits over billions of years. Computer simulations of cosmic structure formation demonstrate that dark matter provides the gravitational seeds around which normal matter accumulates to form galaxies, creating the cosmic web architecture that characterizes large-scale structure throughout the observable universe. These models successfully predict the statistical properties of galaxy distributions, cluster formations, and cosmic void patterns observed through extensive astronomical surveys, confirming that invisible matter dominates cosmic evolution despite its elusive nature. The Milky Way's dark matter halo extends roughly 10 times farther than the visible stellar disk, encompassing a volume where dark particles outnumber ordinary atoms by ratios exceeding 20-1 in the outer regions of our galactic neighborhood. This invisible framework guides the motion of stellar streams, satellite galaxies, and globular clusters through gravitational channels that funnel matter along preferred trajectories while preventing escape from the galaxy's sphere of influence. The complex three-dimensional structure of dark matter distribution creates subtle variations in gravitational potential that influence our solar system's path through galactic space, contributing to the oscillatory motion that carries us alternately above and below the galactic plane over millions of years. Recent theoretical work suggests that dark matter may exist in various forms with different interaction properties, potentially including components that experience forces beyond simple gravitational attraction and creating substructures within galactic halos that could affect local stellar dynamics. Future space missions designed to map dark matter distribution will employ gravitational lensing techniques that detect how invisible mass deflects light from distant background sources, creating distorted images that reveal the presence and configuration of dark matter concentrations. The European Space Agency's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope will survey vast regions of sky to measure these lensing effects with unprecedented precision. building comprehensive maps of dark matter structure that extend from local galactic environments to cosmic scales, sometimes spanning billions of light years. These observations will test competing theories about dark matter's fundamental nature while revealing how invisible cosmic scaffolding connects galactic dynamics to universal structure formation processes. Ground-based experiments continue searching for direct evidence of dark matter particles through underground detectors shielded from cosmic radiation, while particle accelerators attempt to create dark matter candidates under controlled laboratory conditions. The connection between cosmic web architecture and local stellar motions illustrates how dark matter's influence spans scales from subgalactic to supercluster dimensions, creating hierarchical structures where smaller dark matter clumps orbit within larger concentrations while maintaining their individual identities over cosmic timescales. Our solar system's journey through this invisible landscape encounters varying dark matter densities that may influence Earth's cosmic ray environment, potentially affecting atmospheric chemistry and climate patterns through mechanisms that remain subjects of ongoing scientific investigation. The seasonal variation in Earth's galactic velocity creates corresponding changes in our relative motion through the local dark matter distribution, generating annual modulation signals that some experiments claim to detect, while others find no evidence for such effects. These measurements represent humanity's most sensitive attempts to directly observe the invisible substance that dominates cosmic mass while remaining frustratingly elusive to direct detection despite its overwhelming gravitational influence throughout the universe. What mysterious force could overcome the gravitational attraction binding cosmic structures together, and instead drive the fabric of space itself to expand at an accelerating rate that carries distant galaxies away from each other faster than light can travel? The universe undergoes continuous growth through the expansion of space-time itself, a phenomenon that stretches the very medium within which matter and energy exist, while creating additional volume between galactic clusters without requiring objects to move through space in any conventional sense. This cosmic stretching affects every region of the universe simultaneously, from the smallest quantum scales to the largest observable structures, though its effects become noticeable only across distances spanning millions of light years, where gravitational binding forces prove insufficient to resist the relentless outward push of expanding geometry. Edwin Hubble's groundbreaking observations in the 1920s revealed that distant galaxies exhibit systematic redshifts proportional to their distances from Earth, indicating that remote cosmic objects recede from us with velocities that increase linearly with separation according to what became known as Hubble's law. This fundamental relationship demonstrates that space itself grows uniformly in all directions, creating the illusion that Earth occupies a central position in cosmic expansion when actually every observer in the universe would measure identical recession patterns from their respective locations. The Hubble constant quantifies the rate of universal growth, expressing how rapidly space expands per unit distance across cosmic scales, with current measurements indicating that galaxies separated by 1 megaparsec recede from each other at approximately 70 kilometers per second due to intervening space creation. Modern precision measurements by the Hubble Space Telescope, James Webb Space Telescope, and ground-based observatories have refined this value to within a few percent accuracy, while revealing subtle discrepancies between different measurement techniques that suggest either systematic observational errors or new physics beyond current cosmological models. The cosmic expansion creates a temporal hierarchy where nearby galactic clusters remain gravitationally bound despite the underlying space-time stretching, while progressively more distant structures participate increasingly in the general recession that characterizes universal evolution on the largest scales. Our local group of galaxies experiences minimal expansion effects because mutual gravitational attraction between the Milky Way Andromeda and their satellite systems overwhelms the weak expansion forces operating across such relatively small cosmic distances. However, galaxy clusters beyond roughly 100 million light-years participate significantly in cosmic recession, creating observable redshifts that increase with distance according to precisely measurable mathematical relationships that confirm theoretical predictions about universal geometry and evolution. Dark energy represents perhaps the greatest mystery in modern cosmology, comprising approximately 68% of the universe's total energy density while driving accelerated expansion that began roughly 5 billion years ago when cosmic expansion transitioned from deceleration caused by gravitational attraction to acceleration dominated by this enigmatic repulsive force. The discovery of cosmic acceleration through observations of distant supernovae earned the 2011 Nobel Prize in Physics while fundamentally challenging our understanding of cosmic evolution and the ultimate fate of the universe. Current theoretical models propose various explanations for dark energy ranging from Einstein's cosmological constant to exotic quantum fields that pervade empty space, though none have achieved definitive observational confirmation despite intensive research efforts by astronomers worldwide. The acceleration implies that cosmic expansion will continue indefinitely, eventually carrying distant galaxies beyond the observable horizon, where their light can no longer reach Earth, gradually isolating our local group within an increasingly empty cosmic landscape. Earth participates in this universal expansion through its membership in gravitationally bound structures that resist local stretching effects, while remaining embedded within the broader cosmic flow that carries galaxy clusters apart at ever-increasing rates. The expansion affects fundamental physics by stretching electromagnetic radiation to longer wavelengths, cooling the cosmic microwave background radiation that fills all space as a relic from the universe's hot, dense early phases when atoms first formed from primordial plasma approximately 380,000 years after the Big Bang. How does the ancient afterglow of creation itself provide the ultimate cosmic speedometer, revealing Earth's true velocity through the universe by measuring tiny temperature fluctuations in radiation that has travelled unimpeded through space for nearly 14 billion years? The cosmic microwave background represents the cooled remnant of primordial light that filled the universe when it first became transparent approximately 380,000 years after the Big Bang, creating a nearly uniform bath of photons that pervades every cubic centimetre of space, with electromagnetic radiation now shifted to microwave frequencies by cosmic expansion. This relic radiation carries within its subtle temperature variations a precise record of our motion through the cosmos, manifesting as a dipole anisotropy where radiation appears slightly hotter in the direction of our movement and correspondingly cooler in the opposite direction due to relativistic Doppler effects caused by Earth's velocity relative to this primordial photon field. The Cosmic Background Explorer satellite first detected this motion signature in 1989, measuring temperature differences of approximately 3.3 millikelvin between opposite hemispheres of the sky that correspond to our solar system's movement at 368 km per second toward the constellation Leo. This extraordinary precision measurement required sophisticated instruments capable of detecting temperature variations equivalent to distinguishing between ice cubes that differ by 0.003 of a degree, while accounting for foreground contamination from galactic dust, synchrotron emission, and various other astrophysical sources that could mask the subtle cosmological signal. The Wilkinson Microwave Anisotropy Probe refined these measurements during its 9-year mission from 2001 to 2010, creating detailed maps of cosmic microwave background fluctuations that revealed not only our bulk motion through space, but also the primordial density variations that seeded cosmic structure formation throughout the observable universe. These temperature patterns preserve fossil evidence of quantum fluctuations that existed during cosmic inflation, providing our most direct observational window into physical processes that occurred when the universe measured smaller than a subatomic particle, yet contained all the matter and energy visible today. The European Space Agency's Planck mission achieved even greater precision between 2009 and 2013, measuring cosmic microwave background anisotropies with angular resolution and sensitivity that enabled detailed studies of cosmological parameters while confirming our motion through the cosmic rest frame with unprecedented accuracy. The dipole pattern caused by our movement represents the largest amplitude signal in cosmic microwave background data, overshadowing the much smaller primordial fluctuations by factors of hundreds, while demonstrating how local kinematics connects with universal cosmology through observable electromagnetic phenomena. Temperature variations across the sky reveal hierarchical motion components that include Earth's orbital revolution around the Sun, our solar system's galactic trajectory, the Milky Way's movement through the local group, and our local group's bulk flow toward massive gravitational attractors like the Virgo cluster and Great Attractor. Careful analysis allows astronomers to separate these nested velocity components by accounting for known motions and isolating the residual signal that represents our fundamental drift, relative to the cosmic microwave background rest frame. This cosmic rest frame provides the closest approximation to absolute motion that general relativity permits, representing the reference system in which the universe appears most isotropic and homogeneous on the largest, observable scales. The measurement of our cosmic motion through microwave background observations connects local galactic dynamics with universal structure formation, revealing how gravitational clustering creates bulk flows that carry galaxy groups through space along filaments of the cosmic web toward regions of enhanced matter density. Recent studies suggest that our local group participates in an even larger scale flow pattern called the Shapley Attractor supercluster motion, which may account for components of our observed velocity that cannot be explained by nearby gravitational sources alone. The cosmic microwave background also preserves information about the universe's geometry, composition, and evolutionary history through statistical analysis of temperature fluctuation patterns that encode details about dark matter, distributions, baryon acoustic oscillations, and the physics of recombination when neutral atoms first formed from ionized plasma. These observations provide crucial tests of cosmological models while establishing the cosmic microwave background as both a fundamental reference frame for measuring motion and a treasure trove of information about cosmic evolution from the earliest moments after the Big Bang through the present epoch of accelerated expansion driven by mysterious dark energy. What extraordinary complexity emerges when we attempt to combine Earth's rotation, orbital revolution, galactic journey, and cosmic drift into a single coherent description of our planet's total velocity through the universe? And why does this seemingly straightforward calculation require the most sophisticated physics humanity has ever developed? The hierarchical nature of cosmic motion creates nested reference frames, where each larger scale movement carries all smaller scale motions along as passengers, producing intricate velocity relationships that defy intuitive understanding, while demanding relativistic treatments for accurate mathematical description. Earth's axial rotation at roughly 460 meters per second at the equator occurs within the framework of our planet's orbital motion around the Sun at 30 kilometers per second, which itself takes place within our solar system's galactic trajectory at 220 kilometers per second, all of which participate in the local group's cosmic drift at 100 kilometers per second through universal space-time. These nested motions cannot be combined through simple arithmetic addition because velocities in Einstein's relativistic universe follow complex transformation rules that account for the fundamental limit imposed by light speed and the interconnected nature of space and time. Classical Newtonian mechanics would suggest adding these velocity components vectorially to obtain a total speed approaching 850 km per second, but relativistic physics reveals that velocity addition becomes increasingly nonlinear as speeds approach significant fractions of light velocity, requiring special, mathematical formulations that preserve causality while accurately describing high-speed motion. The relativistic velocity addition formula demonstrates that no combination of subluminal speeds can ever produce superluminal motion, regardless of how many velocity components we attempt to combine through successive reference frame transformations. Modern physics recognizes that simultaneity, distance measurements, and time intervals depend upon the observer's motion relative to the phenomena being measured, making the very concept of absolute velocity meaningless, except when specified relative to particular reference frames chosen for convenience or physical significance. The cosmic microwave background provides our best approximation to a universal rest frame representing the reference system in which primordial radiation appears most isotropic, and suggesting a natural coordinate system for measuring cosmic motion despite the absence of truly absolute space or time. Doppler effects, caused by our motion through this radiation field, create observable frequency shifts that enable precise measurements of our velocity components while demonstrating how electromagnetic phenomena connect local kinematics with cosmic evolution. When spacecraft navigate through the solar system, mission planners must account for all these nested motions while calculating trajectories that span months or years, requiring computer models that track multiple moving targets through evolving gravitational fields influenced by planetary positions, solar activity, and relativistic corrections. The global positioning system exemplifies how modern technology accommodates relativistic effects caused by orbital motion and gravitational time dilation, employing atomic clocks that must be continuously adjusted to maintain synchronization despite experiencing different space-time conditions than ground-based receivers. General relativity further complicates motion calculations by revealing that gravity represents curved space-time geometry rather than a conventional force, meaning that objects following geodesic paths through gravitational fields experience no local acceleration despite appearing to accelerate from distant perspectives. The equivalence principle demonstrates that observers falling freely in gravitational fields cannot distinguish their motion from inertial drift through empty space, eliminating absolute distinctions between accelerated and unaccelerated reference frames, while highlighting the observer-dependent nature of motion descriptions. Quantum mechanics adds another layer of complexity by introducing fundamental uncertainties in position and momentum measurements that prevent perfectly precise velocity determinations, while quantum field theory reveals that even empty space contains fluctuating energy densities that interact with moving objects through subtle mechanisms. The interplay between these various physics frameworks creates a comprehensive picture of motion that extends from subatomic scales through cosmic horizons, demonstrating how Earth's journey through space connects with fundamental principles governing reality at every observable level. Modern cosmological models incorporate all these effects when describing how matter moves through expanding space-time, accounting for dark energy acceleration, gravitational clustering, and quantum fluctuations that shaped cosmic structure formation throughout universal history. The mathematical description of hierarchical motion requires tensor calculus, differential geometry, and quantum field theory working together to capture relationships that span more than 40 orders of magnitude in scale, while maintaining internal consistency across the entire range of physical phenomena, from elementary particles to cosmic expansion itself. How will the cosmic choreography that has guided Earth's journey through space for billions of years transform into something utterly unrecognizable as astronomical forces beyond human timescales reshape our galactic neighborhood and ultimately our solar system itself? The trajectory that currently carries our planet through the Milky Way represents merely one brief chapter in a cosmic epic spanning timescales that dwarf geological epochs while connecting stellar evolution, galactic dynamics, and planetary fate through gravitational processes that operate across deep time. Approximately 4.5 billion years from today, the Andromeda Galaxy will collide with the Milky Way in a spectacular merger that will fundamentally alter the gravitational architecture of our local group, while potentially ejecting our solar system from its current orbital configuration through chaotic gravitational interactions between colliding stellar populations. Computer simulations of this galactic encounter reveal complex scenarios where stellar systems experience dramatic orbital changes as competing gravitational fields reorganize matter distributions across scales ranging from individual planetary orbits to cosmic web connections spanning hundreds of millions of light-years. The merger process will unfold over approximately 1 billion years as the two spiral galaxies approach each other, undergo initial gravitational disruption, separate temporally, then merge permanently into a single elliptical system astronomers have dubbed Milkomeda. During these cosmic gymnastics, our solar system may find itself flung into intergalactic space, relocated to distant galactic regions with entirely different stellar neighborhoods, or subjected to close encounters with other stellar systems that could destabilize planetary orbits through gravitational perturbations. Even without external galactic disruption, our Sun's internal nuclear evolution will eventually transform the solar system beyond recognition as hydrogen fuel depletion in the stellar core triggers expansion into a red giant phase approximately a billion years hence. This stellar metamorphosis will increase solar luminosity by factors of thousands while extending the photosphere beyond Earth's current orbital radius, potentially engulfing our planet in stellar atmosphere, or at minimum stripping away our protective atmospheric envelope through enhanced solar wind interactions. The gradual brightening that precedes red giant expansion will begin within the next billion years, increasing terrestrial temperatures sufficiently to vaporize Earth's oceans, while creating runaway greenhouse conditions that render our biosphere uninhabitable long before direct stellar engulfment occurs. These evolutionary timescales challenge human comprehension because they exceed the entire history of complex life on Earth by factors of hundreds while encompassing cosmic changes that operate through physical processes completely removed from biological experience. The deepest geological time represented by Earth's oldest rocks spans roughly 4 billion years, yet stellar and galactic Evolution continues for trillions of years as nuclear fuel supplies, gravitational dynamics, and cosmic expansion create environments vastly different from current conditions. During these extended epochs, the universe itself will undergo profound transformations as accelerated expansion driven by dark energy carries galaxy clusters beyond observable horizons, while stellar formation gradually ceases due to depleted gas reservoirs and gravitational energy dissipation. Proton decay, if it occurs according to some theoretical predictions, will eventually dissolve atomic nuclei over timescales exceeding 10 to 34 years, making the current epoch of stellar burning and planetary existence an infinitesimally brief phase in cosmic history. The connection between cosmic and geological evolution becomes apparent when considering how Earth's changing galactic environment has influenced terrestrial climate, atmospheric composition, and biological evolution throughout geological time. Our solar system's vertical oscillations through the galactic plane expose Earth to varying cosmic ray fluxes, supernova rates, and interstellar medium densities that may correlate with mass extinction events, ice age cycles, and atmospheric chemistry variations preserved in geological records. Future passages through dense molecular clouds or spiral arm regions could alter heliosphere structure, planetary magnetospheres, and atmospheric shielding in ways that dramatically affect Earth's habitability over million-year timescales. The concept of planetary resilience takes on new meaning when viewed against this backdrop of inevitable cosmic change, revealing how temporary the stable conditions that enabled complex life remain relative to the vast transformations awaiting our cosmic neighborhood. Understanding these deep time perspectives provides crucial context for appreciating both the rarity and fragility of habitable worlds, while highlighting how Earth's current journey through space represents an extraordinary cosmic coincidence that has persisted just long enough for intelligence to emerge and contemplate its own cosmic circumstances before stellar and galactic evolution reshapes the playing field entirely. What profound elegance emerges when we recognize that every component of Earth's intricate cosmic journey, from the tiniest quantum fluctuation to the grandest galactic dance, operates according to identical fundamental principles that unite space, time, matter, and energy into a single coherent mathematical framework. The seemingly chaotic complexity of nested planetary motions resolves into breathtaking simplicity when viewed through Einstein's revolutionary insight that gravity represents curved spacetime geometry rather than a mysterious attractive force acting across empty void. General relativity reveals how mass and energy warp the fabric of existence itself, creating geodesic pathways that guide everything from falling apples to orbiting planets to racing galaxies through trajectories determined by local space-time curvature rather than distant gravitational influences. Earth's helical path through the cosmos emerges naturally from this geometric perspective as our planet follows the straightest possible route through a four-dimensional landscape sculpted by the Sun's mass, the galaxy's dark matter distribution, and the universe's expanding metric tensor. The mathematical beauty underlying this description transcends human aesthetic preferences to reveal deep connections between apparently unrelated phenomena, spanning scales from subatomic to cosmological, demonstrating how identical field equations govern planetary orbits, stellar evolution, black hole formation, and cosmic expansion through elegant tensor calculus that captures the essence of gravitational interaction. Local physics determines cosmic trajectories through Einstein's equivalence principle, which demonstrates that gravitational acceleration cannot be distinguished from acceleration caused by applied forces when observed from sufficiently small regions of spacetime. This insight eliminates the conceptual separation between terrestrial and celestial mechanics, while revealing how laboratory experiments conducted on Earth's surface provide direct access to fundamental principles governing motion throughout the observable universe. The inverse square law that describes gravitational attraction between nearby masses represents a low-velocity approximation to relativistic field equations that accurately predict everything from Mercury's orbital precession to gravitational wave propagation from colliding black holes billions of light-years distant. Space-time curvature creates the illusion of gravitational force by establishing preferred directions for motion that objects follow naturally in the absence of non-gravitational influences, much like marbles rolling along curved surfaces without experiencing any mysterious attraction towards specific locations. The unified description of motion through general relativity demonstrates how Earth's complex cosmic trajectory results from our planet's response to gravitational geometry created by overlapping mass distributions across multiple scales, rather than from separate forces operating independently at different cosmic levels. Quantum mechanics adds another layer of unity by revealing how matter and energy represent different manifestations of underlying quantum fields that permeate all space, while creating the mass distributions responsible for space-time curvature through mechanisms described by quantum field theory. The standard model of particle physics and Einstein's gravitational theory together provide a nearly complete description of fundamental interactions that govern everything from atomic structure to galactic clustering, suggesting that Earth's journey through space connects directly with the most basic principles underlying physical reality. Modern cosmology synthesizes these frameworks into comprehensive models that trace cosmic evolution from quantum fluctuations during inflation through structure formation and stellar nucleosynthesis to the emergence of planetary systems capable of supporting complex chemistry and biological evolution. The mathematical description of Earth's path through space thus becomes a window into the deepest workings of nature itself, revealing how local planetary dynamics participates in universal processes that span the entire history of cosmic development, from the Big Bang through the far future when stellar burning ends and black holes evaporate through Hawking radiation. This perspective transforms Earth from an isolated world into an integral component of cosmic evolution, demonstrating how our planet's motion through space connects with fundamental physics, operating at every scale from quantum to cosmological, while preserving the mathematical elegance that characterizes natural law across all observable phenomena throughout the universe. What remarkable practical consequences emerge when engineers apply our understanding of Earth's true cosmic motion to design navigation systems that must function across scales from terrestrial positioning to interstellar exploration, while accounting for relativistic effects that would otherwise introduce catastrophic errors? The global positioning system represents perhaps the most widespread application of relativistic physics in everyday technology, employing atomic clocks aboard satellites that experience measurably different rates of time passage due to their orbital velocities and reduced gravitational potential relative to Earth's surface, without corrections accounting for special and general relativistic effects totaling approximately 38 microseconds per day. GPS receivers would accumulate position errors exceeding 10 kilometers within a single week, rendering the system useless for precise navigation applications. The satellite clocks run faster than terrestrial timepieces due to weaker gravitational fields at orbital altitudes, while simultaneously running slower due to their high orbital velocities, creating competing effects that must be calculated precisely using Einstein's field equations to maintain synchronization across the entire constellation. Deep space mission planning requires even more sophisticated applications of relativistic navigation principles, as spacecraft trajectories spanning years or decades must account for Earth's helical path through galactic space, while predicting planetary positions with extraordinary accuracy, despite the complex gravitational interactions affecting orbital mechanics. The Voyager probes launched in 1977 benefited from careful calculations that incorporated not only planetary orbital mechanics but also subtle corrections for solar motion through the galaxy, enabling these robotic explorers to execute precise gravitational assist maneuvers during their grand tour of the outer solar system. Mission planners recognized that apparent spacecraft trajectories appear dramatically different when viewed from various reference frames, with paths appearing curved or straight depending upon whether observations are made from Earth, the Sun, or the galactic center. The choice of reference frame becomes crucial for trajectory calculations because different coordinate systems simplify or complicate the mathematics required to predict spacecraft motion while highlighting different aspects of orbital dynamics. Earth-centered coordinates prove most convenient for missions within the inner solar system, while heliocentric frameworks better describe interplanetary trajectories, and galactic coordinates become essential for missions venturing beyond the heliopause into interstellar space. The European Space Agency's Gaia mission provides unprecedented precision data about stellar positions and motions that revolutionizes navigation planning for future deep space missions by revealing the true kinematic structure of our galactic neighborhood with micro-arc-second accuracy. This stellar catalog enables mission planners to select optimal reference stars for spacecraft navigation, while accounting for proper motions that accumulate over mission durations measured in decades. Radio astronomy techniques employed for spacecraft communication must compensate for Doppler shifts caused by Earth's complex motion through space, as our planet's seasonal velocity variations create measurable frequency changes in signals exchanged with distant probes. The Deep Space Network stations scattered around Earth's surface experience slightly different Doppler effects due to rotational motion, requiring precise coordination to maintain communication links with spacecraft operating beyond lunar distances. Interstellar missions like Breakthrough Starshot face even greater challenges when attempting to navigate probe swarms travelling at significant fractions of light speed toward nearby stellar systems, as relativistic effects become pronounced, while target stars exhibit proper motions that accumulate over flight times measured in decades. The mathematical complexity of these calculations demands supercomputer resources to model gravitational interactions between multiple bodies, while incorporating relativistic corrections, stellar aberration effects, and the influence of galactic magnetic fields on charged particle trajectories. Pulsar navigation represents an emerging technology that exploits the precise timing of neutron star radio pulses to provide absolute position references for spacecraft operating far from Earth, creating a galactic positioning system independent of terrestrial radio beacons. These cosmic lighthouses emit regular pulses with timing stability exceeding that of atomic clocks, enabling spacecraft to determine their positions within the galaxy by measuring pulse arrival times from multiple pulsars with known positions and proper motions. Future missions to the outer solar system and beyond will increasingly rely upon such autonomous navigation techniques as communication delays with Earth exceed practical limits for real-time guidance. The James Webb Space Telescope demonstrates how modern space missions exploit gravitational dynamics for operational efficiency, maintaining position at the Sun-Earth L2 Lagrange point where gravitational forces balance to minimize fuel consumption while providing continuous observations of the cosmos. Understanding Earth's true motion through space thus transforms from academic curiosity into practical necessity for advancing human presence throughout the solar system and eventual expansion into interstellar space. How has humanity's evolving understanding of Earth's true motion through space fundamentally transformed our philosophical relationship with the cosmos, while simultaneously humbling our cosmic pretensions and elevating our appreciation for the magnificent choreography in which we unknowingly participate? The intellectual journey from geocentric certainty through heliocentric revolution to galactocentric awareness represents more than mere scientific progress. It constitutes a profound philosophical awakening that challenges anthropocentric assumptions while revealing our planet as both cosmically insignificant and extraordinarily privileged. Ancient civilizations naturally assumed Earth occupied the center of creation, with celestial objects revolving around human habitation in arrangements that validated terrestrial importance and divine favor toward our species. This geocentric worldview provided psychological comfort by placing humanity at the focal point of cosmic attention, while making celestial phenomena appear purposefully designed for human observation and interpretation. Copernicus shattered this comforting illusion by demonstrating that Earth orbits the Sun rather than commanding universal reverence, initiating a conceptual revolution that displaced human civilization from cosmic centrality toward peripheral irrelevance within a vast solar system, where terrestrial concerns merit no special consideration from natural forces. The heliocentric model initially preserved some vestige of cosmic significance by suggesting that our solar system might represent the entirety of physical existence, with the Sun serving as the universal center around which all matter revolves in eternal, predictable patterns. However, subsequent discoveries gradually revealed that the Sun itself represents merely one ordinary star among hundreds of billions within a galaxy that spans 100,000 light-years, while containing enough stellar systems to dwarf human comprehension. The recognition of galactic structure further diminished Earth's apparent cosmic importance by demonstrating that our solar system occupies an unremarkable position within a spiral arm of an average galaxy among billions of others scattered throughout observable space. This progressive displacement from cosmic centrality embodies the Copernican principle, which suggests that humans occupy no privileged position within the universe and that physical laws operate identically throughout space and time, regardless of human presence or preferences. Yet this apparent cosmic demotion paradoxically enhances rather than diminishes the wonder of human existence by revealing how extraordinarily improbable and precious our emergence becomes when viewed against the backdrop of cosmic evolution spanning billions of years. The dynamic nature of cosmic motion transforms Earth from a static platform into an active participant in galactic evolution, carrying life and consciousness forward through space on a journey that connects terrestrial biology with stellar nucleosynthesis, supernovas explosions, and cosmic structure formation processes that created the heavy elements essential for planetary chemistry. Our participation in this cosmic dance occurs through no conscious choice or deliberate navigation, but rather represents the inevitable consequence of gravitational dynamics operating across scales, from quantum fluctuations through galactic clustering to universal expansion driven by mysterious dark energy. The beautiful choreography underlying Earth's helical path through space demonstrates how apparent chaos resolves into elegant patterns when viewed from appropriate perspectives with sufficient temporal scope to appreciate the underlying mathematical harmony governing cosmic motion. Modern astronomy reveals that random appearing stellar motions actually follow precise dynamical principles that preserve angular momentum, conserve energy, and maintain gravitational stability across billion-year timescales while creating the spiral structures and cosmic web architectures observable throughout the universe. The philosophical implications of cosmic motion extend beyond scientific curiosity to influence fundamental questions about purpose, meaning, and humanity's relationship with nature itself, suggesting that consciousness represents an emergent property of sufficiently complex matter, configurations that arise naturally through cosmic evolution, rather than requiring supernatural intervention. Scientific discovery transforms human perspective by revealing unexpected connections between local terrestrial phenomena and universal processes operating across cosmic scales, demonstrating how laboratory physics applies directly to stellar interiors, galactic dynamics, and cosmological evolution through identical mathematical frameworks. The progression from geocentric through heliocentric to galactocentric thinking illustrates how expanding observational capabilities and theoretical sophistication gradually unveil deeper layers of cosmic organization while challenging previous assumptions about humanity's place within the cosmic order. Each conceptual revolution initially threatens existing worldviews before ultimately enriching human understanding by revealing previously hidden aspects of natural beauty and mathematical elegance that operate throughout the observable universe. The recognition of Earth's cosmic motion thus represents both humbling acknowledgement of human insignificance relative to galactic scales and profound appreciation for the extraordinary circumstances that enable conscious beings to contemplate their own cosmic journey through space and time. How extraordinary that amid all the cosmic turbulence and celestial complexity we have explored tonight, Earth maintains such remarkable stability that life has flourished for billions of years, while our planet spirals through galactic space at tremendous velocities without ever straying from the narrow habitable zone that permits liquid water to exist. This beautiful paradox reveals how apparent chaos at cosmic scales resolves into gentle, predictable motion when viewed from our terrestrial perspective, where gravitational dynamics create stable orbital relationships that persist across geological timescales despite the intricate dance of multiple simultaneous motions. The same gravitational forces that launch our planet through space at hundreds of kilometers per second also maintain precise distances from the Sun that keep surface temperatures within ranges suitable for complex chemistry, atmospheric retention, and biological evolution throughout Earth's long journey around the galactic center. Our cosmic vessel has carried passengers safely through approximately 18 complete galactic orbits since life first emerged in primordial oceans, navigating through spiral arms, molecular clouds, and varying stellar neighborhoods, while maintaining conditions hospitable enough for single-celled organisms to evolve into the magnificent diversity of species that now inhabit every terrestrial environment from ocean depths to mountain peaks. The stability underlying this apparent motion emerges from conservation laws, governing energy and angular momentum that prevent planetary orbits from degrading significantly over cosmic timescales, creating a reliable cosmic clockwork that operates with precision exceeding any human timepiece. Earth's orbital mechanics demonstrate how complex systems can exhibit emergent stability properties that arise naturally from the mathematical structure of gravitational interactions, rather than requiring careful design or constant adjustment to maintain favorable conditions. The habitable zone around our Sun represents a relatively broad region where liquid water can exist on planetary surfaces, and Earth's slightly elliptical orbit keeps us comfortably within this zone throughout our annual journey, despite seasonal variations in solar distance. Even our solar system's galactic motion contributes to long-term stability by carrying us through regions of space with varying cosmic ray intensities, supernova rates, and interstellar medium densities that may help regulate atmospheric chemistry and climate patterns over millions of years. The vertical oscillations that carry us alternately above and below the galactic plane expose Earth to different galactic environments that could influence evolution through subtle changes in cosmic radiation exposure or gravitational perturbations affecting comet orbits. As we settle into peaceful contemplation tonight, our remarkable planet continues its ancient voyage through space with the same steady reliability that has characterized its motion for billions of years before human consciousness emerged to ponder these cosmic mysteries. While we rest, Earth maintains its rotation rate with an atomic clock precision, preserves its orbital velocity with mathematical exactitude, and participates in galactic motion with the same unwavering dedication that has carried life through countless cosmic seasons. The sunrise that will greet tomorrow morning will illuminate our world from cosmic coordinates never before occupied in the history of the universe. Yet it will appear as familiar and reassuring as countless dawns witnessed by previous generations who remained blissfully unaware of their participation in this grand cosmic voyage. Each breath we take occurs at a unique position in galactic space, making every moment of existence a singular cosmic event that unfolds against the backdrop of stellar evolution, galactic dynamics, and universal expansion, while remaining grounded in the comfortable stability of our terrestrial environment. The gratitude we might feel for this stable platform within dynamic cosmic surroundings extends beyond appreciation for favourable planetary conditions to encompass wonder at the mathematical elegance underlying gravitational dynamics that create order from apparent chaos across every scale of natural phenomena. Our planet serves as both cosmic spacecraft and protective sanctuary, carrying biological cargo safely through environments that would instantly sterilize any exposed organic matter while maintaining atmospheric pressure, temperature, and chemical composition within ranges that support not only survival, but also the complex neural processes that enable consciousness to contemplate its own cosmic circumstances. The journey continues whether we remain awake to observe it or surrender to sleep, while trusting in the same gravitational forces that have guided Earth's path for eons past and will continue determining our cosmic trajectory for eons hence. In this tasteful recognition of our participation in cosmic motion beyond our control or comprehension, we can find comfort in knowing that the universe operates according to reliable physical principles that have created and sustained the extraordinary conditions enabling life to emerge, evolve, and eventually develop the scientific capabilities necessary to understand its own cosmic journey through space and time. What profound tranquility can emerge from recognizing that as our conscious awareness gently dissolves into sleep tonight, Earth will continue its magnificent spiral dance through galactic space with the same graceful precision that has characterized its motion since long before human dreams first stirred in terrestrial minds. While our thoughts slow and breathing deepens into restful rhythms, our planetary home maintains its relentless forward progress through the cosmos, carrying us at velocities that would astonish any wakeful mind yet remain as imperceptible as the passage of dreams themselves. The same gravitational choreography that guided Earth through space billions of years before consciousness emerged from primordial chemistry will continue orchestrating our cosmic voyage throughout the peaceful hours of darkness while we surrender awareness to the restorative mysteries of sleep. Each exhalation releases carbon atoms that once resided in ancient stellar cores, while every inhalation draws oxygen forged in supernovae explosions that occurred millions of years ago when Earth occupied entirely different galactic neighborhoods during its slow spiral around the Milky Way's center. The elements comprising our bodies participated in cosmic evolution spanning eons before assembling into the temporary biological configurations that enable thoughts, dreams, and the capacity for wonder about our place within universal processes that dwarf individual existence, while simultaneously creating the precise conditions necessary for consciousness to arise and contemplate its own cosmic circumstances. As mental activity subsides into the gentle rhythms of sleep, Earth maintains its ancient trajectory through star-filled space. with mechanical reliability that has persisted across geological epochs, ice ages, mass extinction, and the entire evolutionary history that culminated in brains capable of recognizing their participation in galactic motion. The rotation that carries us eastward into tomorrow occurs with atomic clock precision, while our orbital revolution around the Sun progresses according to mathematical relationships discovered by Kepler, yet operating long before human mathematics existed to describe these celestial mechanics. Our solar system's journey through galactic space continues with the same steady determination that has characterized its motion throughout the 4.6 billion years since planetary accretion began, carrying Earth and its cargo of evolving life through cosmic environments that have gradually changed while maintaining the overall stability necessary for biological development. The vertical oscillations that periodically carry our solar system above and below the galactic plane unfold over timescales so vast that entire species arise and disappear between successive passages through the disk's central regions, yet these motions proceed with the same inexorable patience that governs all astronomical processes operating beyond human temporal experience. During sleep, we unconsciously participate in this grand cosmic voyage while dreaming perhaps of journeys to distant worlds, unaware that we already travel among the stars as passengers aboard the most sophisticated spacecraft ever constructed by natural processes. Earth serves as our cosmic vessel, equipped with magnetic shields that deflect harmful radiation, atmospheric protection that maintains stable pressure and temperature, and gravitational anchoring that prevents us from drifting away into the vacuum of space during our high-speed transit through galactic neighborhoods. The dreams that may visit sleeping minds tonight could carry us to imaginary worlds orbiting distant stars, yet even these fictional journeys pale compared to the actual cosmic adventure unfolding as Earth traces its helical path through space at velocities that would tear apart any human-built vehicle, while remaining so smooth that no terrestrial experiment can detect our motion without reference to external astronomical objects. The peaceful acceptance of our role as cosmic passengers creates space for appreciation rather than anxiety about forces and scales beyond human control, recognizing that the same gravitational dynamics carrying us through space also maintain the stable conditions that have enabled life to flourish for billions of years. Tomorrow's awakening will occur at cosmic coordinates never before occupied by Earth throughout its entire history, yet the sunrise will appear as familiar and comforting as countless dawns that have greeted conscious beings throughout human existence. The continuity of experience across this cosmic journey demonstrates how local stability emerges from universal motion, creating reliable patterns within dynamic systems that operate according to physical principles governing everything from quantum mechanics through stellar evolution to cosmic expansion driven by mysterious dark energy. In this gentle recognition of our participation in cosmic processes beyond comprehension, yet fundamental to our existence, sleep becomes not an escape from reality, but a peaceful surrender to the larger rhythms that connect individual consciousness with universal evolution spanning scales from synaptic activity through planetary dynamics to galactic structure formation across billions of years of cosmic history.